out in the void. Where light itself dares not linger, a monster waits. Its hunger is endless. They called it Cygnus X-1. A black hole, but so much more. It's a shadow in the sky, swallowing stars whole. For decades, astronomers searched for proof that these cosmic beasts were real. When Cygnus X-1 revealed itself, it shattered everything we thought we knew about the universe. Its gravity twists reality, bending space and time into impossible shapes. Matter falls toward it, vanishing forever, as if pulled through a doorway to nowhere. This was the first black hole ever truly confirmed. Its discovery rewrote the rules of physics, forcing scientists to confront questions with no answers. What lies beyond the edge of this darkness? What secrets are lost inside? Even now, Cygnus X-1 reminds us there are still places in the universe where our knowledge cannot reach, and maybe never will. Cygnus X-1 is a remarkable cosmic object that has captivated astronomers for decades. Located in the constellation Cygnus, about 6,000 light-years from Earth, it is one of the strongest X-ray sources in our galaxy. This celestial powerhouse is actually a binary system consisting of a blue supergiant star and its mysterious companion. The true nature of Cygnus X-1 was a subject of intense debate among scientists for years. Eventually, observations revealed that the companion object is, in fact, a stellar mass black hole. This black hole, with a mass about 15 times that of our Sun, is locked in a cosmic dance with its stellar partner, drawing material from the star into a swirling accretion disk. As matter from the companion star spirals into the black hole, it heats up to extreme temperatures, emitting powerful X-rays that we can detect from Earth. This process of material accretion and energy release makes Cygnus X-1 one of the brightest X-ray sources in our sky, despite its vast distance from us. The discovery and study of Cygnus X-1 have significantly advanced our understanding of black holes and the extreme physics that govern these enigmatic objects. It serves as a cosmic laboratory, allowing scientists to test theories about gravity, matter, and energy in conditions that cannot be replicated on Earth. Cygnus X-1 was first discovered in 1964 during a rocket flight that carried X-ray detectors high above Earth's atmosphere. This groundbreaking discovery was made by a team of researchers led by Riccardo Giacconi, who would later win the Nobel Prize in Physics for his pioneering work in X-ray astronomy. The object was initially detected as a powerful source of X-rays in the constellation Cygnus, hence its name. At the time of its discovery, the true nature of Cygnus X-1 remained a mystery. Scientists were intrigued by its intense X-ray emissions, which were unlike anything they had observed before. It wasn't until the early 1970s that researchers began to seriously consider the possibility that Cygnus X-1 might be a black hole. This hypothesis was based on its unique characteristics, including its extremely compact size and enormous gravitational pull. The discovery of Cygnus X-1 marked a significant milestone in astrophysics, opening up new avenues for studying some of the most extreme objects in our universe. It continues to be a subject of intense scientific interest and has played a crucial role in our understanding of black holes and high-energy astrophysical phenomena. Cygnus X-1 was first detected as a powerful source of X-rays in 1964 during a rocket flight designed to map cosmic X-ray sources. However, its true nature remained a mystery for several years. The breakthrough in identifying it as a potential black hole came in 1971, thanks to the work of astronomers Thomas Bolton, Louise Webster, and Paul Murdin. Bolton, working at the David Dunlap Observatory in Canada, made crucial observations of the visible star orbiting the unseen X-ray source. He discovered that this star, now known as HDE 226868, was orbiting an invisible companion every 5.6 days. The mass of this unseen object, calculated from the star's orbital motion, was too large to be a neutron star or white dwarf. Webster and Murdin, independently working at the Royal Greenwich Observatory in England, reached similar conclusions. Their observations and calculations also suggested that the invisible companion was too massive to be anything other than a black hole. This marked the first time that astronomers had strong evidence for the existence of a stellar mass black hole in our galaxy. The discovery of Cygnus X-1 as a potential black hole was a watershed moment in astrophysics. It provided the first observational evidence supporting the theoretical concept of black holes, which had been predicted by Einstein's general theory of relativity decades earlier. This finding opened up new avenues of research and sparked intense debate in the scientific community, ultimately leading to our current understanding of black holes as real and ubiquitous objects in the universe. Cygnus X-1, a fascinating cosmic object, lies at a considerable distance from our planet Earth. This remarkable celestial body is located approximately 7,200 light-years away from us. To put this vast distance into perspective, it means that the light we observe from Cygnus X-1 today actually left the object around 7,200 years ago, during the early stages of human civilization on Earth. This enormous separation highlights the immense scale of our galaxy and the challenges astronomers face when studying distant objects. Despite this great distance, Cygnus X-1 remains an object of intense scientific interest due to its unique properties. It is believed to be a binary system consisting of a blue supergiant star orbiting a black hole, making it one of the strongest X-ray sources visible from Earth. The journey to Cygnus X-1 would be an unimaginably long one for any human spacecraft with our current technology. Even light, the fastest known entity in the universe, takes thousands of years to traverse this cosmic gulf. This underscores the vastness of space and the technological hurdles we face in exploring the furthest reaches of our galaxy. Cygnus X-1 stands out as a remarkable celestial object, primarily because it was the first strong candidate for a black hole ever discovered. Located in the constellation Cygnus, this cosmic phenomenon has captivated astronomers since its detection in 1964 during a rocket flight. What truly sets Cygnus X-1 apart is its nature as a binary system. It consists of a blue supergiant star orbiting an invisible companion. This unseen partner is incredibly massive yet compact, exerting a powerful gravitational pull on its stellar neighbor. The intense gravity causes material from the blue supergiant to be stripped away, forming an accretion disk around the hidden object. The most compelling evidence for Cygnus X-1's uniqueness lies in its X-ray emissions. As matter in the accretion disk spirals towards the central object, it heats up to extreme temperatures, releasing intense X-rays. These emissions are far too powerful to be explained by a neutron star or any other known celestial body, leaving a black hole as the most plausible explanation. Cygnus X-1 continues to be a vital subject of study, offering astronomers a rare opportunity to observe and understand the behavior of black holes and their interactions with nearby stars. Its discovery and ongoing analysis have significantly advanced our understanding of these enigmatic cosmic phenomena, cementing its place as a truly unique object in our universe. Cygnus X-1 stands as a pivotal discovery in the field of astrophysics, marking a significant milestone in our understanding of black holes. This cosmic object, first detected in 1964 during a rocket flight, initially puzzled scientists with its intense X-ray emissions. As researchers delved deeper into its nature, Cygnus X-1 emerged as the first strong candidate for a black hole, a concept that had previously existed only in theoretical realms. The importance of Cygnus X-1 lies in its role as observational evidence supporting the existence of black holes. It consists of a binary system where a blue supergiant star orbits an invisible companion. Through meticulous observations and calculations, scientists determined that this unseen object was too massive to be a neutron star, leaving a black hole as the most plausible explanation. This discovery not only confirmed the reality of black holes, but also opened up new avenues for studying these enigmatic cosmic phenomena. Cygnus X-1 provided astronomers with a laboratory to test theories of general relativity and quantum mechanics in extreme gravitational environments. It became a cornerstone for understanding the physics of accretion disks, the swirling matter that surrounds and feeds black holes. Moreover, Cygnus X-1 paved the way for the identification of numerous other black hole candidates throughout the universe. It set the stage for advanced studies of galactic evolution, the life cycles of massive stars, and the fundamental nature of space and time. The landmark status of Cygnus X-1 in astrophysics underscores its crucial role in bridging theoretical predictions with observational astronomy, forever changing our perspective on the cosmos. Cygnus X-1 earned its name through a combination of its location and the nature of its discovery. This cosmic object resides in the constellation Cygnus, which represents a swan in the night sky. The X-1 designation stems from its status as the first X-ray source detected in the Cygnus constellation. Astronomers first identified this mysterious object in 1964 during a rocket flight designed to detect X-ray emissions from space. At the time, scientists were pioneering the field of X-ray astronomy, searching for celestial bodies that emitted X-rays rather than visible light. The discovery of Cygnus X-1 marked a significant milestone in astrophysics. It was one of the earliest and strongest X-ray sources ever detected beyond our solar system. This intense X-ray emission hinted at an extraordinarily energetic phenomenon, which scientists later determined to be a black hole. The naming convention used for Cygnus X-1 became standard practice in X-ray astronomy. As more X-ray sources were discovered in various constellations, they were named similarly, with the constellation name followed by an X and a number indicating the order of discovery within that constellation. Cygnus is a prominent constellation visible in the northern sky during summer and autumn. Its name comes from the Latin word for swan, and its shape resembles a graceful bird with outstretched wings soaring across the Milky Way. Spanning a large area of the celestial sphere, Cygnus contains several bright stars that form a distinctive cross-like pattern, often called the Northern Cross. The brightest star in Cygnus is Deneb, a blue-white supergiant that marks the tail of the swan. Deneb is one of the most luminous known stars, shining with the brightness of over 50,000 suns. Along with Vega in Lyra and Altair in Aquila, Deneb forms the asterism known as the Summer Triangle, a useful navigation tool for stargazers. Cygnus is rich in celestial wonders. It contains the famous binary star Albireo, celebrated for its striking color contrast of gold and blue components when viewed through a telescope. The constellation also hosts the Cygnus Loop, a vast supernova remnant, and numerous star-forming regions along the galactic plane. For astronomers, Cygnus serves as a window into the structure of our galaxy. Its position along the Milky Way band makes it an ideal region for studying star formation, stellar evolution, and the distribution of interstellar matter in our cosmic neighborhood. Cygnus, the Swan constellation, holds a prominent place in various mythologies across cultures. In Greek mythology, it is often associated with the story of Zeus, who transformed himself into a swan to seduce Leda, the queen of Sparta. This tale of divine trickery and mortal beauty has captivated storytellers for centuries. Native American tribes viewed Cygnus differently. The Pawnee people saw the constellation as a bird with outstretched wings, guiding the spirits of the deceased along the Milky Way to the afterlife. This celestial bird served as a spiritual beacon, illuminating the path for souls on their final journey. In Chinese astronomy, Cygnus forms part of a larger celestial pattern known as the Heavenly Ford, representing a bridge across the cosmic river of the Milky Way. This cosmic bridge was said to connect the realms of mortals and immortals, allowing for rare and precious communication between the two worlds. These diverse interpretations of Cygnus demonstrate how ancient cultures looked to the night sky for meaning and guidance. The Swan constellation continues to inspire wonder and speculation, bridging our modern understanding of the cosmos with the rich tapestry of human mythology and imagination. Cygnus X-1 is a remarkable cosmic object located within the boundaries of the constellation Cygnus, also known as the Swan. This celestial connection ties together ancient stellar patterns visible to the naked eye with one of the most intriguing phenomena in modern astrophysics. The constellation Cygnus has been recognized for thousands of years, its cross-like shape reminiscent of a swan in flight. Within this familiar pattern of stars lies Cygnus X-1, an invisible powerhouse that can only be detected through advanced astronomical instruments. Discovered in 1964 during a rocket flight, it was one of the first cosmic X-ray sources ever detected. Cygnus X-1 is now understood to be a binary system consisting of a blue supergiant star and what scientists believe to be a black hole. This pairing creates an intense gravitational dance, with the black hole pulling material from its stellar companion. As this material spirals into the black hole, it heats up to extreme temperatures, emitting powerful X-rays that allow us to detect and study this otherwise invisible cosmic predator. The presence of Cygnus X-1 within the Swan constellation adds a layer of cosmic wonder to this celestial region. It reminds us that even in familiar night sky patterns, extraordinary and extreme phenomena lurk just beyond what our eyes can see, waiting to be uncovered by scientific exploration and technological advancements. Cygnus, the Swan constellation, is home to several fascinating celestial objects beyond its well-known stars. One of the most remarkable is the Cygnus Loop, also known as the Veil Nebula. This vast supernova remnant spans about 110 light-years and consists of delicate filaments of ionized gas, visible as a faint network of glowing threads in the night sky. Another intriguing object in Cygnus is the North America Nebula, named for its striking resemblance to the continent when viewed through a telescope. This enormous cloud of ionized hydrogen gas and dust spans roughly 50 light-years and is a site of active star formation. Nearby, the Pelican Nebula presents another captivating sight, its shape reminiscent of a pelican in flight. Cygnus also harbors the fascinating Cygnus X-1, one of the strongest sources of X-rays in the sky. This region is believed to contain a black hole and is surrounded by an accretion disk of material slowly being drawn in by its immense gravitational pull. The constellation is also home to Cygnus A, one of the brightest radio sources in the sky and one of the first discovered radio galaxies. For those interested in exoplanets, Cygnus offers Kepler-16b, nicknamed Tatooine after the fictional planet in Star Wars. This circumbinary planet orbits two stars, offering a real-world example of a double sunset world. These diverse and captivating objects make Cygnus a treasure trove for astronomers and stargazers alike. Locating Cygnus in the night sky is an exciting endeavor for amateur astronomers. This prominent constellation, also known as the Swan, is one of the most recognizable patterns in the Northern Hemisphere's summer sky. To find Cygnus, start by looking for the Summer Triangle, a large asterism formed by three bright stars, Vega, Deneb, and Altair. Deneb, the brightest star in Cygnus, marks the tail of the Swan and forms one corner of this triangle. Once you've identified the Summer Triangle, focus on Deneb. From there, trace the body of the Swan downward, following a line of stars that forms its long neck. The brightest of these stars is Albireo, which marks the Swan's beak. Perpendicular to this line, you'll see two stars extending on either side, forming the Swan's outstretched wings. The overall shape of Cygnus resembles a cross, which is why it's sometimes called the Northern Cross. This distinctive pattern makes it easier for stargazers to identify, even in areas with moderate light pollution. Cygnus is visible throughout the Northern Hemisphere summer, and can be seen overhead in mid-northern latitudes during the evening hours. For those using star charts or astronomy apps, Cygnus can be found in the Milky Way, between the constellations Lyra and Cepheus. Its prominent position in our galaxy makes it an excellent starting point for exploring other celestial objects, including nebulae and star clusters, with a telescope or binoculars. Cygnus, the celestial swan, has captivated stargazers across cultures for millennia. This prominent northern constellation has been woven into the myths and legends of diverse civilizations, each interpreting its distinctive cross-like shape in unique ways. In ancient Greek mythology, Cygnus was associated with Zeus, who took the form of a swan to seduce Leda, the queen of Sparta. This tale of divine transformation became immortalized in the night sky. The Greco-Roman tradition also linked the constellation to the tragic story of Phaeton, whose friend Cygnus was turned into a swan while mourning his death. Native American cultures saw different figures in these stars. The Cheyenne and Sioux perceived the constellation as an enormous celestial bison, while other tribes envisioned it as a bird flying along the Milky Way, which they called the bird's path. In Chinese astronomy, Cygnus was part of a larger constellation known as Tianjin, the Celestial Ford, representing a bridge of stars spanning the Milky Way. Beyond mythology, Cygnus has played a crucial role in navigation and timekeeping. Deneb, the brightest star in the constellation, has served as an important reference point for travelers throughout history. Its position near the celestial North Pole made it invaluable for determining direction and latitude, guiding both seafarers and land explorers on their journeys across the globe. X-ray astronomy is a fascinating branch of observational astronomy that focuses on detecting and studying celestial objects that emit X-rays. These high-energy electromagnetic waves are invisible to the human eye and cannot penetrate Earth's atmosphere, requiring specialized space-based telescopes to observe them. This field of study allows astronomers to explore some of the most extreme and energetic phenomena in the universe. X-rays are produced by incredibly hot gases, typically millions of degrees in temperature, or by powerful magnetic fields. These conditions exist in a variety of cosmic objects, including neutron stars, black holes, and the remnants of supernova explosions. X-ray astronomy has revolutionized our understanding of the universe since its inception in the 1960s. It has revealed previously unknown features of familiar objects, such as the Sun, and has led to the discovery of entirely new classes of celestial bodies. For instance, X-ray observations have been crucial in identifying and studying binary systems where a normal star orbits a compact object like a neutron star or black hole. One of the most significant contributions of X-ray astronomy has been in the study of galaxy clusters. These observations have revealed vast amounts of hot gas between galaxies, providing crucial insights into the distribution of matter in the universe and the nature of dark matter. As technology advances, X-ray astronomy continues to push the boundaries of our cosmic knowledge, unveiling the hidden, high-energy side of the universe. X-ray astronomy opens up an entirely new window to the universe, revealing cosmic phenomena invisible to traditional optical telescopes. While optical astronomy focuses on the visible light emitted by stars and galaxies, X-ray astronomy detects high-energy radiation produced by some of the most extreme and violent events in space. X-ray telescopes capture emissions from incredibly hot objects and energetic processes. These include the superheated gas swirling around black holes, the remnants of exploded stars, and the vast clouds of scorching gas found in galaxy clusters. Such phenomena often emit little or no visible light, making them undetectable through conventional optical means. The Earth's atmosphere blocks most X-rays from space, necessitating the use of space-based observatories for X-ray astronomy. This requirement has led to the development of specialized satellite telescopes that orbit high above our planet's protective atmospheric shield. These advanced instruments use unique mirror designs and detectors to focus and capture X-ray photons, which behave differently from visible light. X-ray observations complement optical astronomy by providing crucial information about the temperature, composition, and physical processes occurring in cosmic objects. This multispectral approach allows astronomers to build a more comprehensive understanding of the universe, from the life cycles of stars to the evolution of galaxies and the nature of dark matter. X-ray astronomy plays a vital role in our understanding of extreme cosmic objects like Cygnus X-1. These high-energy sources emit most of their radiation in the X-ray part of the electromagnetic spectrum, which is invisible to our eyes and cannot penetrate Earth's atmosphere. This makes X-ray telescopes in space essential for observing and studying these enigmatic celestial bodies. Cygnus X-1, a binary system consisting of a blue supergiant star and a black hole, is a prime example of why X-ray astronomy is crucial. The intense gravitational pull of the black hole strips material from its companion star, forming an accretion disk of superheated gas. This disk reaches temperatures of millions of degrees, causing it to emit powerful X-rays. By studying these X-ray emissions, astronomers can probe the extreme physics occurring near the event horizon of the black hole. X-ray observations of Cygnus X-1 have revealed valuable information about the black hole's mass, spin, and how it interacts with its environment. These studies have also provided insights into the behavior of matter under extreme conditions, helping scientists test and refine theories of general relativity and quantum mechanics. Furthermore, X-ray astronomy has been instrumental in identifying and studying other black holes, neutron stars, and active galactic nuclei throughout the universe. This field continues to push the boundaries of our knowledge, uncovering new mysteries and helping us piece together the cosmic puzzle of our universe's most extreme phenomena. X-ray astronomy became possible through a series of crucial technological advancements in the mid-20th century. The development of rocket technology during and after World War II was a key factor, allowing instruments to be launched above Earth's atmosphere. This was essential because our planet's atmosphere blocks most X-rays from space, making ground-based X-ray astronomy impossible. The invention of Geiger counters and other radiation detectors provided the means to actually detect and measure X-rays from celestial sources. These detectors were initially designed for other purposes, but were adapted for astronomical use. The first X-ray detectors sent to space were simple devices, but they paved the way for more sophisticated instruments. Another critical advancement was the development of grazing incidence mirrors. Unlike visible light, X-rays cannot be focused using conventional lenses or mirrors. Instead, they require special mirrors that reflect X-rays at very shallow angles. This technology, perfected in the 1960s and 70s, allowed for the creation of X-ray telescopes that could produce detailed images of X-ray sources in space. Computer technology also played a vital role. As X-ray detectors and telescopes became more complex, powerful computers were needed to process and analyze the vast amounts of data they produced. This allowed astronomers to create detailed maps and images of the X-ray universe, revealing phenomena invisible to other types of astronomy. X-ray telescopes operate on a unique principle, fundamentally different from optical telescopes. Unlike visible light, X-rays cannot be focused using traditional lenses or mirrors. Instead, these high-energy photons would simply pass through or be absorbed by conventional optical materials. To overcome this challenge, X-ray telescopes employ a technique called grazing incidence. They use specially shaped mirrors arranged in nested cylinders. When X-rays strike these mirrors at a very shallow angle, they reflect off the surface instead of being absorbed. This process is similar to skipping a stone across a pond. The mirrors in X-ray telescopes are typically coated with heavy metals like gold or iridium, which are effective at reflecting X-rays. As the X-rays bounce off multiple mirror surfaces, they are gradually focused toward a detector. This detector then creates an image based on the incoming X-rays. X-ray telescopes must be placed in space because Earth's atmosphere absorbs most X-rays before they reach the ground. By orbiting above our atmosphere, these telescopes can capture X-rays from distant cosmic sources, revealing high-energy phenomena such as black holes, neutron stars, and supernovae remnants that are invisible to optical telescopes. X-ray astronomy faces unique obstacles that set it apart from other forms of astronomical observation. One of the primary challenges is that Earth's atmosphere blocks most X-rays from space, preventing ground-based telescopes from detecting them. This necessitates the use of space-based observatories, which are complex and expensive to build, launch, and maintain. The high-energy nature of X-rays also presents difficulties in focusing and detecting them. Unlike visible light, X-rays cannot be easily reflected or refracted using traditional lenses or mirrors. Instead, astronomers must employ specialized techniques such as grazing incidence optics, where X-rays are reflected at very shallow angles to concentrate them onto detectors. These systems require extremely precise manufacturing and alignment to function effectively. Another hurdle in X-ray astronomy is the relatively low number of photons received from cosmic sources. X-ray emissions are often faint, requiring long observation times and highly sensitive detectors to gather enough data for meaningful analysis. This can limit the number of objects that can be studied in detail and makes it challenging to observe rapid changes in X-ray sources. X-ray emissions often originate from extreme environments such as black holes, neutron stars, and supernovae remnants. Understanding these complex phenomena requires sophisticated models and computational techniques to extract meaningful information from the observed X-ray spectra and images. X-ray astronomy has opened our eyes to a hidden universe, revealing cosmic phenomena invisible to traditional optical telescopes. This groundbreaking field has transformed our understanding of the most energetic and extreme events in space. By detecting high-energy radiation from celestial objects, X-ray astronomy has unveiled the existence of black holes, neutron stars, and other exotic cosmic entities. These observations have allowed scientists to study the intense gravitational fields and powerful magnetic forces at play in the universe, shedding light on fundamental physics in ways previously unimaginable. X-ray telescopes have also revealed vast clouds of superheated gas permeating galaxy clusters. This discovery has led to new insights into the distribution of matter in the universe and the role of dark matter in cosmic structures. Furthermore, X-ray observations have helped astronomers track the life cycles of stars, from their fiery deaths in supernova explosions to the formation of compact stellar remnants. The ability to detect X-rays from distant galaxies has even allowed scientists to probe the early universe, offering glimpses into cosmic history and the evolution of galaxies over billions of years. This revolutionary field continues to push the boundaries of our knowledge, uncovering new mysteries and challenging our understanding of the cosmos with each new observation. Black holes are among the most fascinating objects in the universe. These cosmic phenomena are regions of space where gravity is so intense that nothing, not even light, can escape their pull. They form when massive stars collapse at the end of their lives, condensing an enormous amount of matter into an incredibly small space. At the heart of a black hole lies what scientists call the singularity, a point of infinite density where the laws of physics as we know them break down. Surrounding this is the event horizon, often described as the point of no return. Once anything crosses this boundary, it is forever trapped within the black hole's grasp. Despite their name, black holes are not truly empty voids. They continue to interact with their surroundings, pulling in nearby gas, dust, and even stars. As matter falls into a black hole, it forms a swirling disk of material called an accretion disk. This process can generate immense amounts of energy, making some black holes among the brightest objects in the universe. Black holes come in various sizes, from stellar mass black holes formed from individual stars to supermassive black holes found at the centers of galaxies. These cosmic giants, millions or billions of times more massive than our Sun, play a crucial role in shaping the structure and evolution of galaxies throughout the cosmos. Black holes form when massive stars reach the end of their lives in a spectacular explosion called a supernova. As the star collapses under its own gravity, its core becomes incredibly dense. If the star is massive enough, typically at least 20 times the mass of our Sun, the gravitational force becomes so intense that nothing can escape its pull, not even light. The boundary beyond which nothing can escape is called the event horizon. Once matter crosses this point, it is forever lost to the outside universe. As the black hole continues to consume nearby gas, dust, and even entire stars, it grows larger and more powerful. In some cases, black holes can also form when two neutron stars collide. These dense stellar remnants spiral towards each other, releasing enormous amounts of energy in the form of gravitational waves. When they finally merge, the combined mass can be sufficient to create a new black hole. Supermassive black holes, found at the centers of most galaxies, are thought to form through a different process. These giants, millions or billions of times more massive than stellar black holes, likely grew over billions of years by consuming vast amounts of matter and merging with other black holes. Black holes come in a range of sizes, each with unique characteristics. Stellar black holes form when massive stars collapse at the end of their lives. These cosmic objects typically have masses between 5 and several dozen times that of our Sun. They're relatively common, with millions potentially scattered throughout our galaxy. Supermassive black holes dwarf their stellar counterparts. These giants lurk at the centers of most galaxies, including our own Milky Way. They can contain millions or even billions of solar masses. Scientists believe these behemoths grow by merging with other black holes and consuming vast amounts of matter over billions of years. Intermediate mass black holes bridge the gap between stellar and supermassive varieties. With masses ranging from about 100 to 1 million times that of the Sun, these elusive objects have proven challenging to find and study. Astronomers suspect they might form in dense star clusters or result from the merger of smaller black holes. Primordial black holes represent a hypothetical class that may have formed in the extreme conditions of the early universe. These could range from microscopic sizes to masses comparable to small stars. While their existence remains unproven, they offer intriguing possibilities for explaining dark matter and other cosmic mysteries. The event horizon of a black hole marks a critical boundary in space. It is the point of no return, where the gravitational pull becomes so intense that nothing, not even light, can escape. This invisible barrier surrounds the black hole, separating the observable universe from the black hole's interior. At the event horizon, the laws of physics as we understand them begin to break down. Time and space become warped in extreme ways, leading to mind-bending phenomena. For an outside observer, an object falling towards the event horizon appears to slow down and freeze in time, never quite reaching the boundary. The size of an event horizon depends on the mass of the black hole. For a stellar black hole formed from the collapse of a massive star, the event horizon might be just a few kilometers across. In contrast, supermassive black holes at the centers of galaxies can have event horizons millions or billions of kilometers in diameter. Studying the event horizon presents immense challenges for scientists. Its nature makes direct observation impossible, forcing researchers to rely on indirect methods and complex simulations to understand this cosmic frontier. Despite these obstacles, the event horizon continues to captivate astronomers and push the boundaries of our understanding of the universe. At the heart of every black hole lies a mystery that continues to baffle scientists: the singularity. This enigmatic point represents the ultimate extreme in our universe, where the laws of physics as we know them break down. The singularity is believed to be infinitely dense, containing all the mass of the black hole compressed into an unimaginably small space. As matter and light fall into a black hole, they are inexorably drawn toward this central point, where gravity becomes infinite and space-time curves in on itself. What makes the singularity so perplexing is that our current understanding of physics cannot fully explain what happens there. The extreme conditions at the singularity are beyond anything we can observe or replicate on Earth, making it a frontier of scientific exploration. Some theories suggest that the singularity might be a gateway to other universes or different regions of our own universe. Others propose that quantum effects might prevent true singularities from forming. As we continue to study black holes, we edge closer to unraveling the secrets of these cosmic enigmas and potentially revolutionizing our understanding of the universe itself. Black holes are cosmic powerhouses that dramatically warp the fabric of space-time. As we approach a black hole, its immense gravitational pull begins to stretch and distort everything around it. This warping effect becomes more pronounced the closer we get, ultimately leading to what scientists call gravitational time dilation. Time itself slows down near a black hole. If we could observe someone falling towards the event horizon, the boundary beyond which nothing can escape, we would see them appear to move more slowly. From their perspective, however, time would seem to pass normally, while the rest of the universe would appear to speed up. Space, too, is profoundly affected. The black hole's gravity is so strong that it bends light itself. This creates a phenomenon known as gravitational lensing, where objects behind the black hole can appear distorted, magnified, or even duplicated from our viewpoint. The fabric of space becomes so curved that paths of light that would normally be straight now follow curved trajectories. At the event horizon, these effects reach their extreme. Space becomes so warped that even light cannot escape, and time, as we understand it, essentially stops. This boundary marks the point of no return, beyond which our current laws of physics break down, and the mysteries of quantum gravity take hold. Black holes are considered black because they do not emit or reflect any light. Their immense gravitational pull is so strong that nothing, not even light itself, can escape once it crosses the event horizon. This boundary marks the point of no return, where the escape velocity exceeds the speed of light. The extreme nature of black holes means that all incoming light and matter are trapped forever, unable to reach our eyes or instruments. As a result, black holes appear as dark voids against the backdrop of space, earning their name from this light-absorbing quality. Interestingly, while black holes do not emit light directly, they can be detected through indirect means. Matter falling into a black hole forms an accretion disk, which heats up to extreme temperatures and emits intense radiation. This glow from the surrounding area often serves as a telltale sign of a black hole's presence. Despite their name, black holes are far from empty. They contain an enormous amount of mass compressed into an incredibly small space, warping the fabric of space-time itself. This combination of extreme density and gravitational influence makes black holes some of the most fascinating and mysterious objects in our universe. The discovery of Cygnus X-1 began with the advent of X-ray astronomy in the 1960s. Scientists used high-altitude balloons and rockets to carry X-ray detectors above Earth's atmosphere, which blocks most cosmic X-rays from reaching the ground. During these observations, they detected a strong X-ray source in the constellation Cygnus. This X-ray source, later named Cygnus X-1, stood out due to its intense and variable emission. Unlike other known X-ray sources at the time, Cygnus X-1 showed rapid fluctuations in brightness, changing on timescales as short as milliseconds. This variability suggested that the X-ray emitting region must be extremely compact, no larger than a few hundred kilometers across. Further observations revealed that Cygnus X-1 was paired with a visible star, a blue supergiant called HDE 226868. Measurements of this star's motion indicated it was orbiting an unseen companion every 5.5 days. The invisible object's gravitational influence on the blue supergiant implied it was incredibly massive, at least 6 times the mass of our Sun. These combined observations, the intense X-ray emission, rapid variability, and high mass, led scientists to propose that Cygnus X-1 might be the first detected black hole. This hypothesis sparked intense debate and further study, ultimately leading to the acceptance of Cygnus X-1 as one of the most convincing candidates for a stellar mass black hole in our galaxy. The discovery and identification of Cygnus X-1 involved several scientists working across different fields of astronomy. In 1964, a suborbital rocket flight detected a strong X-ray source in the constellation Cygnus, which was later catalogued as Cygnus X-1. This initial detection was made by a team led by Riccardo Giacconi, an Italian-American astrophysicist who later won the Nobel Prize for his pioneering work in X-ray astronomy. The true nature of Cygnus X-1 remained a mystery for several years. In 1971, Paul Murdin and Louise Webster, 2 astronomers working at the Royal Greenwich Observatory, made a crucial breakthrough. They identified a blue supergiant star called HD 226868 as the visible companion to the X-ray source, suggesting that Cygnus X-1 was part of a binary system. Around the same time, Thomas Bolton, a Canadian astronomer, independently made similar observations. Bolton's work provided strong evidence that the invisible companion to the blue supergiant was too massive to be a neutron star, leading to the groundbreaking conclusion that it must be a black hole. This marked the first time a black hole had been identified through observations. The collaborative efforts of these scientists, along with subsequent observations and analyses by many others in the astronomical community, solidified Cygnus X-1's status as the first strong black hole candidate. Their work opened up new avenues for studying these enigmatic cosmic objects and significantly advanced our understanding of the universe. Cygnus X-1 was first detected in 1964 during a rocket flight that carried Geiger counters into the upper atmosphere. These early instruments were crucial in identifying this powerful source of X-rays in the constellation Cygnus. Following this initial discovery, astronomers used a variety of increasingly sophisticated tools to study Cygnus X-1 in greater detail. Radio telescopes played a significant role, allowing scientists to observe the object across different wavelengths and gather more information about its nature. Optical telescopes also contributed to our understanding of Cygnus X-1 by revealing its visible companion star, a blue supergiant. This discovery was key to understanding the binary system nature of Cygnus X-1. As technology advanced, space-based X-ray observatories like the Uhuru satellite and later missions such as Chandra and XMM Newton provided unprecedented views of Cygnus X-1. These instruments allowed astronomers to study its X-ray emissions in great detail, leading to the compelling evidence that Cygnus X-1 contains a black hole, a conclusion that revolutionized our understanding of these exotic cosmic objects. Cygnus X-1 first caught the attention of astronomers in the 1960s when it was detected as a powerful source of X-rays. This discovery was intriguing because X-ray emissions often indicate extreme cosmic events or objects. As scientists studied Cygnus X-1 more closely, they noticed several key characteristics that pointed towards the presence of a black hole. One crucial observation was the detection of a blue supergiant star in a binary system with an invisible companion. The visible star appeared to be orbiting around a massive yet unseen object. By analyzing the star's orbital motion, scientists calculated that the invisible companion must be incredibly dense and compact, with a mass several times that of our Sun. The X-ray emissions provided another vital clue. The intensity and pattern of these emissions suggested that material from the visible star was being pulled towards the unseen object, forming an accretion disk. As this material spiraled inward, it heated up to extreme temperatures, producing the observed X-rays. This behavior is consistent with what scientists expect to see around a black hole. Furthermore, the rapid variability of the X-ray emissions indicated that the source region must be very small, ruling out larger cosmic objects like neutron stars. These combined observations led scientists to conclude that Cygnus X-1 likely contained a black hole, making it one of the first strong black hole candidates identified in our galaxy. When astronomers first detected Cygnus X-1 in the 1960s, it sparked intense debate and skepticism within the scientific community. This powerful source of X-rays, located in the constellation Cygnus, exhibited properties that defied conventional explanations. Many researchers were reluctant to accept the most plausible interpretation, that Cygnus X-1 was a black hole. The idea of black holes, objects so dense that not even light could escape their gravitational pull, had been a theoretical concept for decades. However, the prospect of actually observing one seemed far-fetched to many scientists. Some argued that the X-ray emissions could be explained by other astronomical phenomena, such as neutron stars or white dwarfs. The skepticism was further fueled by the implications of confirming the existence of black holes. Such a discovery would validate aspects of Einstein's theory of general relativity and fundamentally change our understanding of the universe. As a result, numerous alternative theories were proposed and debated, with scientists meticulously analyzing the data to find any possible explanation that did not involve a black hole. This initial doubt and rigorous scrutiny ultimately led to more comprehensive observations and studies of Cygnus X-1. Over time, as evidence accumulated and technology improved, the scientific consensus shifted. The skepticism surrounding Cygnus X-1 gradually gave way to acceptance, marking a pivotal moment in our understanding of the cosmos and the exotic objects that inhabit it. The journey to accept Cygnus X-1 as a black hole was a fascinating process that unfolded over several decades. Discovered in 1964 during a rocket flight, Cygnus X-1 initially puzzled astronomers with its intense X-ray emissions. At the time, the concept of black holes was still largely theoretical, and many scientists were skeptical about their existence. Throughout the 1970s, evidence began to mount, suggesting that Cygnus X-1 might indeed be a black hole. Observations revealed it was part of a binary system with a blue supergiant star, and its behavior matched theoretical predictions for a black hole. However, alternative explanations, such as a neutron star, were still considered possible. The debate intensified in the scientific community, with some prominent physicists, including Stephen Hawking, initially betting against Cygnus X-1 being a black hole. It wasn't until the 1990s that a growing consensus began to form. Improved observational techniques and more sophisticated theoretical models provided stronger evidence for the black hole interpretation. By the early 2000s, most astronomers accepted Cygnus X-1 as a black hole. The final confirmation came in 2011, when precise measurements of its mass and other properties left little doubt about its nature. This acceptance marked a significant milestone in our understanding of these enigmatic cosmic objects, transforming them from theoretical curiosities to observable realities. A binary star system consists of two stars orbiting around their common center of mass. These stellar pairs are bound together by gravity, engaged in an eternal cosmic dance. Binary stars are remarkably common in our galaxy, with current estimates suggesting that more than half of all stars exist in such systems. In a binary star system, the two stars can have varying masses, sizes, and evolutionary stages. Some binary pairs are visible to the naked eye, appearing as a single point of light that can only be resolved into two distinct stars with the aid of a telescope. Others are so close together that even our most advanced instruments struggle to separate them. The interactions between stars in a binary system can lead to fascinating phenomena. In some cases, one star may draw matter from its companion, potentially triggering spectacular novae or even supernova explosions. Binary stars also play a crucial role in our understanding of stellar evolution and the fundamental properties of stars. Studying binary star systems helps astronomers measure stellar masses and distances with greater precision than is possible with single stars. This knowledge has far-reaching implications, informing our comprehension of galaxy formation, stellar populations, and the broader cosmic landscape. Cygnus X-1 is a remarkable binary star system located about 6,000 light-years from Earth in the constellation Cygnus. This system consists of two main components: a blue supergiant star and a black hole, locked in a cosmic dance around each other. The blue supergiant, known as HDE 226868, is an enormous star about 40 times more massive than our Sun. It's in the late stages of its stellar life, rapidly burning through its fuel and shedding its outer layers. This process feeds material to its companion, the black hole. The black hole in Cygnus X-1 is a stellar mass black hole, estimated to be about 21 times the mass of our Sun. Its intense gravitational pull draws in material from the blue supergiant, forming an accretion disk of superheated gas swirling around the black hole. As this material falls towards the black hole, it releases enormous amounts of energy, particularly in the form of X-rays. This powerful X-ray emission is what makes Cygnus X-1 so notable. It was one of the first discovered X-ray sources in the sky and provided some of the strongest early evidence for the existence of black holes. The system continues to be a valuable subject for studying the physics of black holes and the extreme environments they create. Cygnus X-1 is a fascinating binary star system located in the constellation Cygnus, about 6,000 light-years from Earth. The system consists of a black hole and a blue supergiant star, which is the companion star in question. This massive star, known as HDE 226868, is roughly 40 times more massive than our Sun and has a surface temperature of about 30,000 Kelvin. The blue supergiant orbits the black hole every 5.5 days, locked in a cosmic dance that has captivated astronomers for decades. As the companion star orbits, it loses mass to the black hole through stellar winds and direct transfer of material. This process creates an accretion disk around the black hole, which heats up to extreme temperatures and emits powerful X-rays. The relationship between the black hole and its companion star provides scientists with a unique opportunity to study the behavior of matter in extreme gravitational fields. By observing the X-ray emissions and the orbital motions of the system, researchers can gain insights into the properties of black holes and the physics of accretion. Cygnus X-1 stands as a testament to the dynamic and often violent nature of stellar evolution, showcasing the fate that awaits many massive stars in our universe. The blue supergiant companion, though currently the more visible of the pair, is destined to eventually be consumed by its black hole partner, further fueling this cosmic powerhouse. Black holes and their companion stars engage in a cosmic dance of gravity and matter. When a black hole orbits close to a star, its immense gravitational pull begins to strip away the star's outer layers. This process, known as stellar stripping, creates a stream of gas flowing from the star towards the black hole. As this gas approaches the black hole, it forms a swirling disk of material called an accretion disk. The gas in this disk heats up to extremely high temperatures due to friction and compression, causing it to glow brightly across various wavelengths of light. This intense radiation can be detected by our telescopes, allowing astronomers to identify and study these binary systems. The black hole does not consume all the incoming material at once. Instead, some of the gas and dust from the accretion disk can be ejected at high speeds, forming powerful jets that extend far into space. These jets can influence the surrounding interstellar medium and even affect star formation in nearby regions. Over time, the continuous loss of mass can dramatically alter the companion star. In some cases, the star may be completely consumed by the black hole. In others, the interaction may leave behind a smaller, denser stellar remnant. This ongoing exchange of matter and energy between the black hole and its companion star provides astronomers with valuable insights into the life cycles of stars and the growth of black holes. The Cygnus X-1 system, a fascinating cosmic duo, completes its orbital dance in approximately 5.5 days. This binary system consists of a blue supergiant star and a black hole locked in a gravitational embrace, circling each other at an astonishing pace. The rapid orbital period is a result of the intense gravitational forces at play between these two massive objects. This swift rotation provides astronomers with frequent opportunities to study the system, offering insights into the behavior of matter around black holes. As the blue supergiant star orbits the black hole, it transfers material to its dark companion, creating a swirling accretion disk that emits powerful X-rays. These emissions allow scientists to track the orbital motion and study the extreme physics at work in this cosmic laboratory. The short orbital period of Cygnus X-1 stands in stark contrast to many other binary star systems, which can take weeks, months, or even years to complete a single orbit. This rapid rotation highlights the extraordinary nature of this system and its importance in our understanding of black hole physics and stellar evolution. Cygnus X-1 offers astronomers a unique opportunity to study black holes up close. This binary system consists of a massive blue supergiant star orbiting an invisible companion, which scientists have identified as a stellar mass black hole. The close dance between these two objects provides a wealth of information about the nature and behavior of black holes. The regular orbital motion of the visible star allows scientists to calculate the mass of its unseen partner. By observing the star's movement and applying the laws of gravity, researchers can determine that the invisible object must be incredibly dense and compact, matching the theoretical predictions for a black hole. Furthermore, the interaction between the star and the black hole creates observable phenomena that reveal more about the black hole's properties. As the black hole pulls material from its companion star, this matter forms an accretion disk around the black hole. The extreme temperatures in this disk cause it to emit X-rays, which we can detect and study from Earth. These X-ray emissions provide valuable data about the black hole's size, spin, and how it interacts with surrounding matter. The binary nature of Cygnus X-1 also allows scientists to study how black holes affect their immediate environment. By observing changes in the companion star and the space around the binary system, researchers can better understand the powerful gravitational effects of black holes and how they shape the evolution of nearby stars and interstellar matter. An accretion disk is a remarkable cosmic structure that forms around massive objects in space, such as black holes, neutron stars, and even young stars in the process of formation. These disks are made up of gas, dust, and other materials that are gradually pulled in by the strong gravitational force of the central object. As matter spirals inward, it flattens out into a rotating disk shape due to conservation of angular momentum. This process is similar to how a figure skater spins faster when they pull their arms close to their body. The inner regions of the accretion disk move faster than the outer parts, causing friction and generating intense heat. In the case of black holes, accretion disks can reach temperatures of millions of degrees, causing them to emit powerful radiation across the electromagnetic spectrum. This makes them some of the brightest objects in the universe, often outshining entire galaxies. Accretion disks play a crucial role in the growth and evolution of cosmic objects. They provide a mechanism for matter to be funneled onto the central body, allowing it to increase in mass over time. In the case of forming stars, these disks can also be the birthplaces of planets, making them essential to our understanding of how solar systems like our own come into existence. Cygnus X-1, a famous black hole in our galaxy, showcases a remarkable accretion disk that forms through a fascinating cosmic dance. This disk is created as the black hole pulls material from its companion star, a blue supergiant. The intense gravitational force of the black hole causes the stellar material to spiral inward, forming a flattened disk of gas and dust around the black hole. As the material in the disk orbits closer to the black hole, it heats up due to friction and compression. This heating process causes the disk to glow brightly in X-rays, making Cygnus X-1 one of the strongest X-ray sources in our sky. The inner regions of the disk can reach temperatures of millions of degrees, creating a turbulent and dynamic environment. The accretion process is not uniform, with some areas of the disk becoming denser and hotter than others. This leads to instabilities and fluctuations in the X-ray emissions we observe from Earth. The disk also plays a crucial role in feeding the black hole, as some of the material eventually crosses the event horizon and adds to the black hole's mass. Understanding the formation and behavior of accretion disks like the one in Cygnus X-1 provides valuable insights into the extreme physics around black holes. It also helps scientists study how black holes grow and influence their surroundings, shaping the evolution of galaxies over cosmic time. Cygnus X-1, a prominent X-ray source in our galaxy, owes much of its intense radiation to its accretion disk. This disk forms as material from a nearby companion star is drawn towards the black hole at the center of Cygnus X-1. As this matter spirals inward, it heats up due to friction and compression, reaching temperatures of millions of degrees. At these extreme temperatures, the disk material becomes so energetic that it emits X-rays. The inner regions of the accretion disk, closest to the black hole, produce the most energetic X-rays due to the intense gravitational forces and highest temperatures in this area. These X-rays can escape the system and travel across space, allowing us to detect them here on Earth. The accretion disk also plays a crucial role in shaping the overall X-ray spectrum we observe from Cygnus X-1. Different parts of the disk emit X-rays at varying energies, creating a complex emission profile. Additionally, some X-rays from the innermost regions of the disk can be scattered or reflected off other parts of the disk or surrounding gas, further modifying the observed spectrum. Studying these X-ray emissions provides valuable insights into the physics of black holes and the extreme environments around them. The accretion disk acts as a natural laboratory, allowing scientists to test theories about matter behavior under conditions impossible to replicate on Earth. Relativistic jets are powerful streams of matter and energy that shoot out from the cores of certain galaxies and quasars at nearly the speed of light. These extraordinary phenomena are closely linked to supermassive black holes that reside at the centers of these cosmic objects. As material swirls around the black hole in a disk of gas and dust, Some of it gets accelerated and ejected along the axis of rotation, forming two narrow beams that extend far into intergalactic space. These jets can stretch for millions of light-years, dwarfing their host galaxies and acting as cosmic beacons visible across vast distances. The material within these jets is heated to extreme temperatures and emits intense radiation across the electromagnetic spectrum, from radio waves to gamma rays. This makes relativistic jets some of the most energetic and luminous objects in the universe. The term relativistic refers to the incredible speeds at which the particles in these jets travel, approaching the speed of light. At such velocities, the effects of Einstein's special relativity become apparent, causing time dilation and length contraction from the perspective of an outside observer. This relativistic motion also results in an effect called relativistic beaming, where the radiation is concentrated in the direction of the jet's motion, making them appear even brighter when viewed head-on. Studying relativistic jets provides astronomers with valuable insights into the physics of black holes, the properties of matter under extreme conditions, and the evolution of galaxies. These cosmic fountains play a crucial role in redistributing energy and matter throughout the universe, influencing the formation and growth of cosmic structures on grand scales. Cygnus X-1, a well-known black hole system, produces powerful jets of material that stretch for thousands of light-years. These jets form through a complex interplay of gravity, magnetic fields, and the extreme conditions near the black hole's event horizon. The process begins with the black hole's intense gravitational pull, which draws in material from its companion star. This material forms a swirling disk of gas and dust around the black hole, known as an accretion disk. As the material in this disk spirals inward, it heats up to incredibly high temperatures due to friction and compression. Near the black hole's event horizon, magnetic fields become intensely concentrated and twisted. These fields interact with the hot, ionized material in the accretion disk, channeling some of it away from the disk and accelerating it to nearly the speed of light. This accelerated material is then ejected from the system's poles, forming the observed jets. The exact mechanisms behind jet formation are still not fully understood, but scientists believe that the interplay between the black hole's rotation, the accretion disk's magnetic fields, and the extreme gravitational forces all contribute to this spectacular phenomenon. Ongoing research continues to refine our understanding of these powerful cosmic beacons. Cygnus X-1 offers astronomers a unique laboratory for studying the extreme physics of black holes and their interactions with surrounding matter. The powerful jets emanating from this system provide crucial insights into the processes occurring near the event horizon of stellar mass black holes. By observing these jets, scientists can better understand how black holes convert the gravitational energy of infalling matter into kinetic energy, launching particles at nearly the speed of light. The composition and structure of these jets reveal information about the accretion disk surrounding the black hole and the intense magnetic fields that help shape and accelerate the outflows. Furthermore, studying Cygnus X-1 allows researchers to test theories of general relativity in strong gravitational fields. The behavior of matter and energy in the vicinity of the black hole can be used to verify predictions made by Einstein's theory and explore potential deviations that might point to new physics. The jets of Cygnus X-1 also provide valuable data on the interaction between black holes and their companion stars in binary systems. This information helps astronomers understand the evolution of such systems and the role they play in shaping galactic environments over cosmic timescales. Cygnus X-1 is a remarkable binary star system that showcases the fascinating interplay between an accretion disk and powerful jets. At the heart of this system lies a stellar mass black hole, voraciously consuming matter from its companion star. As this material spirals inward, it forms a swirling accretion disk around the black hole. The interaction between the accretion disk and jets in Cygnus X-1 is a dynamic process driven by intense gravitational and magnetic forces. As matter in the disk loses angular momentum, it heats up to extreme temperatures, emitting X-rays and other forms of high-energy radiation. Some of this superheated material doesn't fall into the black hole, but instead gets channeled into two narrow, opposing jets that shoot out perpendicular to the disk. These jets are thought to be powered by the rotational energy of the black hole itself, extracted through complex magnetic processes in the accretion disk. The jets can reach speeds close to that of light and extend for thousands of light years into space. They act as cosmic particle accelerators, propelling matter and energy far from the black hole. The relationship between the disk and jets is not one way. The powerful outflows from the jets can influence the structure and behavior of the accretion disk, creating a feedback loop that helps regulate the overall system. This intricate dance between inflow and outflow makes Cygnus X-1 an invaluable laboratory for studying the extreme physics of black holes and their environments. Cygnus X-1 stands as a cosmic enigma that pushes the boundaries of our understanding of physics. This powerful X-ray source, located in the constellation Cygnus, is believed to be a black hole orbited by a blue supergiant star. Its existence and behavior have forced scientists to reconsider fundamental aspects of astrophysics and general relativity. The extreme nature of Cygnus X-1 provides a unique laboratory for testing the limits of our physical theories. Its intense gravitational field warps spacetime to such a degree that it allows us to observe relativistic effects predicted by Einstein's theories. These observations include the bending of light and the distortion of time itself, phenomena that are difficult to study in less extreme environments. Furthermore, Cygnus X-1 challenges our understanding of how matter behaves in the presence of incredibly strong gravitational fields. The accretion disk surrounding the black hole heats up to millions of degrees, emitting X-rays and providing insights into the behavior of plasma under extreme conditions. This has led to new theories about the mechanisms driving astrophysical jets and the processes by which black holes consume matter. The study of Cygnus X-1 also raises questions about the formation and evolution of massive stars and black holes. Its existence suggests that some massive stars can collapse directly into black holes without first exploding as supernovae, a process that was previously thought to be unlikely. This revelation has implications for our understanding of stellar evolution and the distribution of black holes throughout the universe. Cygnus X-1, a well-known binary star system, serves as a cosmic laboratory for testing several key aspects of Einstein's theory of general relativity. This system consists of a blue supergiant star orbiting what scientists believe to be a black hole, providing an excellent opportunity to observe extreme gravitational effects. One crucial aspect of general relativity tested by Cygnus X-1 is the behavior of space and time in strong gravitational fields. The intense gravity near the black hole causes significant distortions in spacetime, allowing scientists to study how light and matter behave in these extreme conditions. Observations of Cygnus X-1 have confirmed the gravitational redshift predicted by Einstein, where light leaving the vicinity of the black hole loses energy and shifts towards longer wavelengths. Additionally, Cygnus X-1 allows researchers to examine the frame-dragging effect, also known as the Lentz-Thirring effect. This phenomenon, predicted by general relativity, occurs when a massive rotating object like a black hole drags the fabric of spacetime around it. By studying the X-ray emissions from the accretion disk surrounding the black hole, scientists can detect signs of this frame-dragging effect. Furthermore, Cygnus X-1 provides an opportunity to test the no-hair theorem, a key prediction of general relativity, stating that black holes can be completely described by just three parameters: mass, spin, and electric charge. Detailed observations of the system help scientists verify whether this simplification holds true in nature, furthering our understanding of black hole physics and the fundamental principles of Einstein's groundbreaking theory. Cygnus X-1, a binary star system containing a black hole, challenges our understanding of quantum mechanics in profound ways. This cosmic laboratory, located roughly 6,000 light-years from Earth, provides a unique opportunity to study extreme physics. The black hole in Cygnus X-1 is so dense that it warps spacetime to an extraordinary degree. This intense gravitational field creates conditions where quantum effects and general relativity intersect, pushing our theories to their limits. Scientists are particularly interested in what happens at the event horizon, the boundary beyond which nothing can escape the black hole's grip. One intriguing aspect is Hawking radiation, a theoretical quantum effect where particles can escape from a black hole. While this phenomenon is too faint to observe directly in Cygnus X-1, studying the system helps refine our models and predictions. The extreme environment also allows us to test quantum entanglement, the spooky action at a distance that Einstein found so perplexing on cosmic scales. Moreover, Cygnus X-1 challenges our notions of information conservation in quantum mechanics. As matter falls into the black hole, the information it carries seemingly vanishes, contradicting a fundamental principle of quantum theory. This information paradox remains unresolved, with Cygnus X-1 serving as a cosmic testing ground for potential solutions, driving physicists to develop new theories that merge quantum mechanics with gravity. Cygnus X-1 presents several intriguing paradoxes that challenge our understanding of extreme cosmic phenomena. This powerful X-ray source, believed to be a black hole, defies conventional expectations in ways that continue to perplex astronomers. One paradox involves the intense radiation emitted by Cygnus X-1. Black holes are known for their immense gravity that prevents even light from escaping. Yet Cygnus X-1 is one of the brightest X-ray sources in our galaxy. This seeming contradiction arises from the interaction between the black hole and its companion star. As matter from the companion is pulled towards the black hole, it forms an accretion disk that heats up to extreme temperatures, emitting powerful X-rays before crossing the event horizon. Another puzzling aspect of Cygnus X-1 is its rapid variability. The X-ray emissions from this system can change dramatically in mere fractions of a second, suggesting that the source of these emissions must be incredibly compact. This rapid flickering challenges our understanding of the processes occurring near the event horizon of a black hole, where extreme gravitational effects distort space and time. The existence of Cygnus X-1 itself presents a paradox when considering stellar evolution. The black hole in this system is thought to have formed directly from the collapse of a massive star without a supernova explosion. This formation scenario contradicts our typical understanding of how black holes are created, highlighting the complex and often counterintuitive nature of these cosmic phenomena. Cygnus X-1 stands as a cosmic laboratory, pushing our understanding of physics to its limits. This binary system, consisting of a blue supergiant star orbiting a black hole, provides astronomers with a unique opportunity to study extreme gravitational environments. The intense gravitational pull of the black hole in Cygnus X-1 creates conditions that cannot be replicated on Earth. As matter from the companion star falls towards the black hole, it forms an accretion disk that heats up to millions of degrees. This process releases enormous amounts of energy, particularly in the form of X-rays, allowing scientists to observe and analyze the behavior of matter in the presence of incredibly strong gravitational fields. Observations of Cygnus X-1 have helped confirm predictions made by Einstein's theory of general relativity. The system's behavior aligns closely with what we expect to see in the vicinity of a black hole, including the warping of spacetime and the presence of an event horizon. These observations provide crucial empirical support for our current understanding of gravity and spacetime. Furthermore, Cygnus X-1 offers insights into the formation and evolution of black holes and massive stars. By studying this system, scientists can refine models of stellar evolution and improve our understanding of the life cycles of the most massive stars in the universe. This knowledge, in turn, helps us explore the limits of our physical laws and pushes us to develop new theories that can explain the extreme phenomena we observe in the cosmos. Recent observations of Cygnus X-1 have led to intriguing new theories about this famous black hole system. Scientists have proposed that the black hole in Cygnus X-1 might be spinning close to the maximum rate allowed by general relativity. This rapid rotation could be causing extreme distortions in the fabric of spacetime around the black hole, influencing how matter and energy behave in its vicinity. Another fascinating theory suggests that Cygnus X-1 might be producing powerful jets of particles that extend far beyond the binary system. These jets could be interacting with the surrounding interstellar medium in ways we have not previously understood, potentially affecting the evolution of nearby star-forming regions. Researchers have also put forward the idea that the accretion disk around the black hole in Cygnus X-1 might be more complex than initially thought. Some propose that it could have multiple layers with different properties, each interacting with radiation and matter in unique ways. This multi-layered structure could explain some of the variable X-ray emissions observed from the system. Additionally, there are new hypotheses about the companion star in the Cygnus X-1 system. Some scientists suggest that it might be in a more advanced stage of stellar evolution than previously believed, which could have implications for our understanding of how such binary systems form and evolve over time. Cygnus X-1, a binary star system located about 6,000 light-years from Earth, harbors one of the most studied black holes in our galaxy. The black hole in this system is a stellar mass black hole formed from the collapse of a massive star. Recent observations and calculations have refined our understanding of this cosmic behemoth. The black hole in Cygnus X-1 is estimated to have a mass of around 21 times that of our Sun. This makes it one of the most massive stellar black holes discovered in our Milky Way galaxy. To put this into perspective, if we were to replace our Sun with this black hole, its gravitational influence would extend far beyond the orbit of Mars, dramatically altering the structure of our solar system. Despite its enormous mass, the black hole itself is incredibly compact, with a radius of only about 60 kilometers. The massive nature of this black hole allows it to pull material from its companion star, a blue supergiant, creating a swirling disk of matter around it. As this material falls into the black hole, it heats up and emits powerful X-rays, making Cygnus X-1 one of the brightest X-ray sources in our sky and a valuable target for astronomers studying the extreme physics of black holes. Cygnus X-1 stands out as one of the most massive stellar black holes ever discovered. Its enormous size places it at the upper end of the mass range for black holes formed from the collapse of individual stars. Scientists estimate that Cygnus X-1 weighs in at around 21 times the mass of our Sun, making it significantly heavier than many other known stellar black holes. To put this into perspective, the average mass of stellar black holes in our galaxy is thought to be between 5 and 15 times the mass of the Sun. This means Cygnus X-1 is substantially larger than most of its cosmic counterparts. However, it is important to note that supermassive black holes, which reside at the centers of galaxies, are on an entirely different scale, often millions or billions of times more massive than Cygnus X-1. The exceptional mass of Cygnus X-1 has intrigued astronomers since its discovery. It challenges our understanding of stellar evolution and the processes that form black holes. Scientists continue to study this cosmic behemoth to unravel the mysteries of how such massive stellar black holes come into existence and how they affect their surrounding space. Scientists employ several sophisticated techniques to estimate the mass of Cygnus X-1, a well-known black hole in our galaxy. One primary method involves studying the orbital dynamics of the binary system in which Cygnus X-1 resides. By observing the motion of the visible companion star, astronomers can deduce the gravitational influence of the unseen black hole. Spectroscopic measurements play a crucial role in this process. Scientists analyze the light from the companion star, looking for periodic shifts in its spectral lines. These shifts, caused by the Doppler effect, reveal how fast the star is moving towards and away from Earth as it orbits the black hole. This information, combined with the orbital period, allows researchers to calculate the mass function of the system. Another important technique is the analysis of X-ray emissions from the accretion disk surrounding Cygnus X-1. As matter from the companion star falls towards the black hole, it heats up and emits X-rays. The patterns and intensity of these emissions provide clues about the black hole's mass and spin. Advanced computer models also contribute to mass estimations. Scientists input observational data into these models, which simulate the behavior of binary systems under various conditions. By comparing model predictions with actual observations, researchers can refine their estimates of Cygnus X-1's mass, gradually narrowing down the range of possible values. The event horizon of Cygnus X-1, one of the most studied black holes in our galaxy, is remarkably compact. This stellar mass black hole has an event horizon that spans approximately 60 kilometers in diameter. To put this into perspective, that's about the length of 6.5 football fields laid end to end. Despite its relatively small size, the gravitational influence of Cygnus X-1 extends far beyond its event horizon. The black hole's immense gravity warps the fabric of space-time in its vicinity, creating a region where nothing, not even light, can escape once it crosses this boundary. The size of a black hole's event horizon is directly related to its mass. Cygnus X-1 is estimated to have a mass around 15 times that of our Sun, compressed into this incredibly dense, compact object. This concentration of mass creates a gravitational field so intense that it defines the very edge of what we can observe. Interestingly, while we cannot directly see beyond the event horizon, the effects of Cygnus X-1 on its surroundings, including its companion star and the material it pulls in, allow scientists to study and understand the nature of this cosmic behemoth. The small yet mighty event horizon of Cygnus X-1 continues to be a subject of fascination and intensive research in the field of astrophysics. Cygnus X-1, a famous black hole in our galaxy, dwarfs our solar system in scale. This cosmic behemoth has a mass about 15 times that of our Sun, but its size is incredibly compact. The event horizon of Cygnus X-1, the boundary beyond which nothing can escape its gravitational pull, is estimated to be only about 90 kilometers in diameter. Despite its relatively small physical size, the influence of Cygnus X-1 extends far beyond its event horizon. Its immense gravitational field affects a much larger area, creating an accretion disk of hot gas and dust that spans a region larger than our entire solar system. This disk, glowing brightly with X-rays, stretches over millions of kilometers. For comparison, our solar system, measured to the edge of the Oort cloud, is believed to extend about 2 light-years from the Sun. This means that while the visible part of Cygnus X-1 is incredibly compact, its gravitational influence reaches across a volume that could encompass thousands of solar systems like ours. The stark contrast between the compact nature of Cygnus X-1 and its far-reaching effects illustrates the extreme nature of black holes. It reminds us that in the cosmos, size does not always correlate with influence, and some of the smallest objects can have the most profound impact on their surroundings. Scientists studying Cygnus X-1 encounter several significant challenges when attempting to measure its properties. This binary star system, consisting of a blue supergiant star and a black hole, presents unique obstacles due to its extreme nature and distant location. One major difficulty lies in accurately determining the mass of the black hole. While scientists can observe the movements of the visible star, the black hole itself remains invisible. They must rely on indirect measurements and complex calculations to estimate its mass, which introduces a degree of uncertainty. Another challenge is the intense X-ray emissions from the system. These emissions, produced as matter from the supergiant star, falls into the black hole, can overwhelm and distort other measurements. Scientists must develop sophisticated techniques to filter out this noise and obtain clear data about the system's other properties. The extreme distances involved also pose problems. Cygnus X-1 is located roughly 6,000 light-years from Earth, making precise measurements challenging. Even small errors can lead to significant discrepancies in our understanding of the system. Despite these obstacles, ongoing advancements in technology and observational techniques continue to improve our ability to study this fascinating cosmic laboratory. Cygnus X-1, a stellar mass black hole in our galaxy, exerts an immense gravitational influence on its surroundings. This cosmic behemoth, with a mass about 15 times that of our Sun, warps the fabric of space-time in extraordinary ways. The intense gravity of Cygnus X-1 creates a deep curvature in spacetime, much like a heavy ball on a stretched rubber sheet. This curvature becomes more pronounced as you approach the black hole, reaching extreme levels near its event horizon. The event horizon marks the point of no return, where the warping of spacetime is so severe that nothing, not even light, can escape. As matter and light approach Cygnus X-1, they follow the curved paths dictated by this warped spacetime. This phenomenon leads to fascinating effects, such as gravitational lensing, where light from distant objects behind the black hole can be bent and magnified, creating multiple or distorted images. The spacetime distortion near Cygnus X-1 also causes time dilation. An observer far from the black hole would see time passing much more slowly for objects closer to it. This effect becomes more pronounced the nearer an object gets to the event horizon, demonstrating the profound connection between gravity, space, and time in the universe. Gravitational lensing is a fascinating phenomenon that occurs when the gravity of a massive object bends the path of light from a distant source. This effect can magnify, distort, or even create multiple images of the background object. It's like looking through a giant cosmic magnifying glass, allowing astronomers to observe celestial bodies that would otherwise be too faint or distant to detect. In the case of Cygnus X-1, gravitational lensing plays an indirect but important role. Cygnus X-1 is a binary star system containing a blue supergiant star and what scientists believe to be a black hole. While gravitational lensing isn't directly observed in Cygnus X-1 itself, the concept helps us understand and study black holes like the one in this system. The intense gravitational field of a black hole can cause extreme lensing effects, bending light to such a degree that it orbits the black hole multiple times before escaping or being pulled in. This creates a phenomenon known as the photon ring, a bright circle of light that surrounds the black hole's event horizon. Although we can't directly observe this effect in Cygnus X-1 due to its relatively small size and great distance, studying gravitational lensing in other systems helps scientists refine their models of black hole behavior. Furthermore, gravitational lensing has been crucial in detecting and studying other black holes throughout the universe. By observing how light bends around these massive objects, astronomers can infer their presence and properties even when the black holes themselves remain invisible. This technique has significantly advanced our understanding of black holes, including those similar to the one believed to exist in Cygnus X-1. Cygnus X-1, a powerful black hole in our galaxy, exerts a tremendous gravitational influence on its surroundings. This cosmic behemoth, with a mass about 15 times that of our Sun, warps the fabric of spacetime around it, creating a gravitational field that affects the motion of nearby stars and gas. The most noticeable impact is on its binary companion, a blue supergiant star. This massive star orbits Cygnus X-1 in an elliptical path, its movement a cosmic dance dictated by the black hole's gravity. The black hole's intense pull causes the star to lose mass over time, with stellar material flowing towards Cygnus X-1 in a process called accretion. Beyond its immediate companion, Cygnus X-1 influences the movement of interstellar gas and dust in its vicinity. The black hole's gravity can capture and heat this material, forming an accretion disk that spirals inward. This process not only affects the distribution of matter in the surrounding space, but also generates powerful X-ray emissions that can be detected from Earth. While its gravitational influence is strong, the effects of Cygnus X-1 on more distant objects are less pronounced. Stars and other celestial bodies farther away experience a much weaker pull, their movements shaped more by the overall gravitational field of the Milky Way galaxy than by this singular black hole. Nevertheless, Cygnus X-1 remains a fascinating example of how extreme objects can shape their cosmic neighborhoods. If our Sun were suddenly replaced by Cygnus X-1, the consequences for our solar system would be both immediate and catastrophic. Cygnus X-1 is a binary star system consisting of a blue supergiant star and a black hole located about 6,000 light-years from Earth. The black hole in this system is estimated to have a mass around 15 times that of our Sun, while its companion star is roughly 40 times more massive than our star. The immense gravitational pull of the black hole would immediately disrupt the orbits of all planets in our solar system. Earth and the other inner planets would likely be pulled inward and eventually consumed by the black hole. The gas giants like Jupiter and Saturn might be torn apart by tidal forces before meeting a similar fate. The intense radiation emitted by the accretion disk around the black hole would be lethal to all life on Earth long before the planet was destroyed. This disk, formed by material from the companion star falling toward the black hole, produces powerful X-rays and other high-energy radiation that would strip away our atmosphere and bombard the surface with deadly particles. Furthermore, the presence of the massive blue supergiant companion star would introduce additional gravitational and radiative effects, further destabilizing the solar system and contributing to its rapid destruction. Replacing our stable, life-supporting Sun with the volatile and extreme Cygnus X-1 system would spell the end of our solar system as we know it. Cygnus X-1, a powerful X-ray source in our galaxy, serves as an ideal cosmic laboratory for testing Einstein's theory of general relativity. This system consists of a massive blue supergiant star orbiting an extremely dense object, which scientists believe to be a stellar mass black hole. The immense gravitational pull of this compact object provides a unique opportunity to observe and measure relativistic effects in action. The intense gravity around Cygnus X-1 causes significant distortions in spacetime, allowing researchers to study phenomena predicted by general relativity. One such effect is the gravitational redshift, where light escaping from near the black hole's event horizon is stretched to longer wavelengths due to the extreme gravitational field. By precisely measuring this redshift, scientists can compare the observations with theoretical predictions, thereby testing the accuracy of general relativity in strong gravitational environments. Another important aspect of Cygnus X-1 for testing general relativity is the behavior of matter in its accretion disk. As material from the companion star spirals towards the black hole, it forms a rapidly rotating disk. The innermost stable circular orbit of this disk, as predicted by general relativity, depends on the black hole's mass and spin. By studying the X-ray emissions from this region, researchers can verify if the observed orbital dynamics match the theoretical expectations. Furthermore, the binary system of Cygnus X-1 allows scientists to measure the frame dragging effect, also known as the Lentz-Thirring effect. This phenomenon, where a rotating massive object drags spacetime around it, causes precession in the orbit of the companion star and the accretion disk. By carefully analyzing these orbital changes over time, researchers can further test the predictions of general relativity in the strong field regime, pushing our understanding of gravity to new limits. Frame dragging is a fascinating phenomenon predicted by Einstein's theory of general relativity. It occurs when a massive rotating object like a black hole twists the fabric of spacetime around it, similar to how a spinning ball would drag a rubber sheet. This effect causes nearby objects and even light to be pulled along in the direction of the rotation. Cygnus X-1, a well-known binary system containing a black hole, provides an excellent opportunity to observe frame dragging in action. The black hole in this system is rotating at an incredibly high speed, nearly half the speed of light. As it spins, it drags the surrounding spacetime with it, creating a sort of cosmic whirlpool. Scientists have detected the effects of frame dragging in Cygnus X-1 by observing the behavior of the accretion disk, a swirling collection of gas and dust that surrounds the black hole. The inner part of this disk is being pulled along by the rotating spacetime, causing it to precess or wobble like a spinning top. This precession occurs at a rate that matches the predictions made by general relativity for frame dragging. The observations of Cygnus X-1 not only confirm the existence of frame dragging, but also provide valuable insights into the properties of black holes and the nature of spacetime itself. By studying systems like this, scientists can continue to test and refine our understanding of gravity and the fundamental workings of the universe. X-ray variability refers to the changes in intensity and energy of X-ray emissions from celestial objects over time. This phenomenon is observed in various cosmic sources, including black holes, neutron stars, and active galactic nuclei. The fluctuations can occur on timescales ranging from milliseconds to years, providing astronomers with valuable insights into the physical processes and structures of these extreme objects. In the case of black holes, X-ray variability often results from matter spiraling into the black hole through an accretion disk. As this material heats up to extremely high temperatures, it emits X-rays. The intensity of these emissions can change rapidly due to variations in the accretion rate or instabilities in the disk itself. For neutron stars, X-ray variability may be caused by changes in the star's magnetic field or by material falling onto its surface. These variations can reveal information about the neutron star's rotation, magnetic properties, and interactions with its environment. Studying X-ray variability allows scientists to probe the innermost regions of these cosmic objects, areas that are often too small or distant to observe directly. By analyzing the patterns and characteristics of these fluctuations, researchers can deduce important information about the size, mass, and behavior of some of the most extreme objects in our universe. Cygnus X-1, a powerful X-ray source in our galaxy, exhibits fascinating variability in its emission. This celestial object, known to be a black hole in a binary system with a blue supergiant star, displays both rapid fluctuations and longer-term changes in its X-ray output. On short timescales, Cygnus X-1 shows rapid flickering in its X-ray brightness. These quick variations occur within fractions of a second to several seconds, reflecting the turbulent nature of matter as it swirls into the black hole. Scientists believe these rapid changes are due to instabilities in the accretion disk, the swirling ring of hot gas surrounding the black hole. Over longer periods, ranging from days to months, Cygnus X-1 transitions between two main states. In the hard state, it emits more high-energy X-rays, while in the soft state, it produces more low-energy X-rays. These state changes are thought to be related to variations in the rate at which matter falls into the black hole and changes in the structure of the accretion disk. Astronomers have also observed occasional X-ray flares from Cygnus X-1, where its brightness can increase dramatically for short periods. These events provide valuable insights into the extreme physics occurring near the black hole's event horizon, where the gravitational pull becomes so strong that not even light can escape. Cygnus X-1, a famous black hole system in our galaxy, exhibits fascinating X-ray variability that has intrigued astronomers for decades. This variability is primarily caused by the complex interactions between the black hole and its companion star. The black hole in Cygnus X-1 is constantly pulling matter from its companion, a blue supergiant star. This matter forms an accretion disk around the black hole, swirling inward at incredible speeds. As the material in the disk heats up to millions of degrees, it emits X-rays. The intensity of these X-rays can change rapidly, sometimes within fractions of a second. Several factors contribute to this variability. Instabilities in the accretion disk can cause fluctuations in the amount of matter falling into the black hole, leading to changes in X-ray emission. Additionally, the inner regions of the disk can undergo rapid changes in temperature and density, further affecting the X-ray output. Another significant factor is the corona, a region of hot electrons above the accretion disk. This corona can scatter lower-energy photons from the disk, boosting them to X-ray energies. Changes in the structure or temperature of the corona can lead to rapid variations in the observed X-ray intensity. These complex processes combine to create the dynamic X-ray behavior that makes Cygnus X-1 such a captivating object of study for astronomers. Scientists employ a variety of sophisticated techniques to study the X-ray variability of Cygnus X-1, a well-known black hole binary system. Space-based X-ray telescopes, such as NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton, play a crucial role in these observations. These advanced instruments allow researchers to detect and measure the high-energy radiation emitted by the accretion disk surrounding the black hole. One key method involves collecting data over extended periods, sometimes spanning days or even weeks. This long-term monitoring enables scientists to create detailed light curves, which show how the X-ray brightness of Cygnus X-1 changes over time. These fluctuations can occur on timescales ranging from milliseconds to hours, providing valuable insights into the complex processes taking place near the black hole. Researchers also utilize sophisticated statistical techniques to analyze the observed variability patterns. Fourier analysis, for example, helps break down the complex variations into different frequency components, revealing periodic oscillations that might be linked to orbital motions or other regular processes in the system. Additionally, scientists study the energy spectrum of the X-rays, which can change as the overall brightness fluctuates, offering clues about the physical conditions in the accretion disk. By combining these various approaches and comparing the results with theoretical models, astronomers can gain a deeper understanding of the extreme environment around the black hole in Cygnus X-1. This includes insights into the structure of the accretion disk, the behavior of matter as it falls toward the black hole, and the mechanisms driving the powerful X-ray emissions we observe from Earth. X-ray variability provides a powerful tool for peering into the hidden depths of black holes. As matter spirals towards these cosmic behemoths, it heats up to extreme temperatures, emitting intense X-rays that fluctuate in brightness over time. By analyzing these fluctuations, scientists can uncover crucial information about the structure and behavior of black holes. One key insight gained from X-ray variability is the size of the region closest to the black hole, known as the event horizon. Rapid changes in X-ray brightness indicate that the emitting region must be incredibly compact, allowing researchers to estimate the black hole's mass and spin. This technique has revealed that supermassive black holes at the centers of galaxies can weigh millions or even billions of times more than our Sun. X-ray variability also sheds light on the complex interactions between black holes and their surrounding environment. Patterns in the fluctuations can reveal the presence of accretion disks, swirling vortexes of gas and dust that feed the black hole. Scientists have even detected quasi-periodic oscillations, rhythmic pulses in X-ray brightness that may be caused by matter orbiting near the event horizon or vibrations in the accretion disk itself. Furthermore, studying X-ray variability across different timescales allows astronomers to probe various regions around the black hole. Rapid fluctuations originate from areas closest to the event horizon, while slower changes can be traced to outer parts of the accretion disk or even the broader galactic environment. This multi-scale approach provides a comprehensive view of black hole systems, from their innermost structures to their effects on surrounding space. Cygnus X-1 stands out among black holes for its distinctive X-ray variability patterns. This stellar mass black hole, located approximately 6,000 light-years from Earth, exhibits rapid and intense fluctuations in its X-ray emissions on timescales ranging from milliseconds to days. These variations are significantly more pronounced and frequent than those observed in many other black hole systems. The X-ray emissions from Cygnus X-1 are characterized by abrupt, powerful flares that can increase the object's brightness by factors of 10 or more within seconds. These intense bursts are interspersed with periods of relative quiescence, creating a highly dynamic and unpredictable emission profile. This behavior contrasts sharply with the more stable or slowly varying X-ray output seen in many other black hole systems, particularly supermassive black holes at the centers of galaxies. The rapid variability of Cygnus X-1 is thought to be linked to the complex interactions between the black hole, its accretion disk, and its binary companion star. As matter from the companion star falls towards the black hole, it forms a swirling accretion disk. Instabilities in this disk, combined with the intense gravitational and magnetic fields near the black hole, lead to the observed X-ray fluctuations. Scientists studying Cygnus X-1 have used its unique variability patterns to gain insights into the extreme physics occurring near the event horizon of stellar mass black holes. This has made Cygnus X-1 an invaluable laboratory for testing theories of general relativity and understanding the behavior of matter in extreme gravitational fields, setting it apart from many other black hole systems in our galaxy. The event horizon is a crucial concept in our understanding of black holes. It marks the boundary beyond which nothing, not even light, can escape the black hole's intense gravitational pull. This invisible barrier surrounds the black hole, acting as a cosmic point of no return. At the event horizon, the gravitational force becomes so strong that the escape velocity equals the speed of light. Since nothing can travel faster than light, anything that crosses this threshold is forever trapped within the black hole. This includes matter, energy, and even information itself. The size of an event horizon depends on the mass of the black hole. For a stellar black hole, which forms from the collapse of a massive star, the event horizon might be just a few kilometers across. In contrast, supermassive black holes at the centers of galaxies can have event horizons millions or even billions of kilometers in diameter. Interestingly, an observer falling into a black hole would not notice anything special upon crossing the event horizon. However, to an outside observer, time would appear to slow down for objects approaching the event horizon, eventually freezing at the boundary itself. This time dilation effect is a consequence of Einstein's theory of general relativity and highlights the profound impact black holes have on the fabric of spacetime. Cygnus X-1, the first discovered black hole candidate, has been a subject of intense study for astronomers since its detection in 1964. While we have not directly observed its event horizon, we have made significant progress in understanding this fascinating cosmic object. Using a network of radio telescopes called the Event Horizon Telescope, scientists have achieved unprecedented resolution in observing Cygnus X-1. This powerful array has allowed us to peer closer to the black hole than ever before, revealing intricate details of its surrounding environment. Recent observations have provided insights into the accretion disk, the swirling matter around the black hole, and the powerful jets of material ejected from its poles. These observations have helped refine our estimates of the black hole's mass and spin, crucial parameters that influence its behavior and the spacetime around it. While we have not yet captured an image of Cygnus X-1's event horizon itself, our current observations bring us tantalizingly close. As technology advances and our understanding deepens, we inch ever closer to unveiling the secrets hidden at the very edge of this cosmic abyss. As an object approaches the event horizon of Cygnus X-1, a stellar mass black hole in our galaxy, it enters a realm where the laws of physics are pushed to their limits. The immense gravitational pull of the black hole begins to dominate every aspect of the object's existence. Time itself starts to slow down from the perspective of a distant observer, while the object experiences extreme tidal forces that stretch and compress it. Once the object crosses the event horizon, it enters a point of no return. No information or matter can escape from beyond this boundary, not even light. The object would be subjected to ever-increasing gravitational forces as it continues its journey towards the singularity at the center of the black hole. These forces would cause the object to be stretched vertically and compressed horizontally in a process astronomers call spaghettification. As the object descends deeper into the black hole, the differences in gravitational pull between its leading and trailing edges become so extreme that it would be torn apart at the atomic level. The material that once made up the object would be added to the mass of the black hole, increasing its size by a minuscule amount. From the perspective of an outside observer, the object would appear to slow down and freeze as it approaches the event horizon due to the extreme time dilation effects of the black hole's gravity. Its image would also become increasingly redshifted and dimmer, eventually fading from view entirely. This fascinating interplay of extreme physics demonstrates the profound impact of supermassive objects on the fabric of spacetime itself. As we approach the event horizon of Cygnus X-1, a stellar mass black hole, time begins to behave in ways that defy our everyday understanding. The immense gravitational pull of this cosmic titan warps the fabric of spacetime itself, causing time to slow down dramatically for objects near the event horizon compared to distant observers. This phenomenon, known as gravitational time dilation, becomes increasingly pronounced the closer one gets to the event horizon. An observer far from Cygnus X-1 would perceive time passing much more quickly for themselves than for an object or person nearing the black hole's point of no return. At the event horizon itself, time essentially grinds to a halt from an outside perspective. If we could somehow observe an object falling into Cygnus X-1, it would appear to freeze in time at the event horizon, never quite crossing it from our vantage point. This effect is due to the extreme curvature of spacetime caused by the black hole's intense gravity. For an object or observer falling past the event horizon, however, time would continue to flow normally from their perspective. They would cross the boundary in a finite amount of time according to their own clock, even as outside observers see them frozen at the edge for what seems like eternity. This stark contrast in the experience of time showcases the profound impact of extreme gravity on the very nature of our universe. The information paradox is a perplexing problem in physics that arises when we consider what happens to information that falls into a black hole. At the heart of this paradox lies a conflict between two fundamental principles of physics: quantum mechanics and general relativity. According to quantum mechanics, information cannot be destroyed. Every particle carries specific information about its quantum state, and this information should be preserved over time. However, when matter falls into a black hole, it seems to vanish completely once it crosses the event horizon, the boundary beyond which nothing can escape the black hole's gravitational pull. General relativity, on the other hand, suggests that anything crossing the event horizon is lost forever, along with all its information. This appears to violate the principles of quantum mechanics, creating a paradox. The problem becomes even more complex when we consider Hawking radiation, the theoretical process by which black holes slowly evaporate over time. If a black hole eventually disappears, what happens to all the information it consumed? Physicists have proposed various solutions to this paradox, including the idea that information might be encoded on the event horizon itself, or that it could somehow leak out through quantum entanglement. However, a complete resolution to the information paradox remains one of the most challenging and intriguing questions in modern physics, pushing our understanding of the universe to its limits. Observing the event horizon of Cygnus X-1 presents a significant challenge due to its immense distance from Earth, approximately 6,000 light-years away. However, advancements in astronomical technology offer promising avenues for future direct observation. One potential method involves using very long baseline interferometry, a technique that combines data from multiple radio telescopes across the globe to create a virtual telescope with extraordinary resolution. The Event Horizon Telescope project, which captured the first image of a black hole in Messier 87, could potentially be expanded or enhanced to target Cygnus X-1. Another approach might utilize X-ray interferometry in space. By deploying a network of satellites equipped with high-precision X-ray detectors, scientists could potentially create an X-ray interferometer capable of resolving the event horizon of Cygnus X-1. This would require overcoming significant technical hurdles, including precise positioning and synchronization of the satellites. Future developments in gravitational wave detection might also play a role. As our ability to detect and interpret gravitational waves improves, we may be able to glean information about the structure and behavior of the event horizon through the gravitational signals emitted by Cygnus X-1 and its companion star. Hawking radiation is a remarkable phenomenon theorized by the renowned physicist Stephen Hawking. This concept challenges our understanding of black holes, those cosmic behemoths once thought to be the ultimate cosmic prisons from which nothing could escape. According to Hawking's groundbreaking work, black holes are not entirely black. They actually emit a faint glow of particles, now known as Hawking radiation. This radiation occurs due to quantum effects near the event horizon, the boundary beyond which nothing can escape a black hole's gravitational pull. At the quantum scale, pairs of particles and antiparticles constantly pop into existence, usually annihilating each other almost instantly. However, near a black hole's event horizon, one particle might fall into the black hole, while the other escapes. The escaping particle becomes the Hawking radiation, while the infalling particle, with negative energy, reduces the black hole's mass. This process leads to a profound implication. Black holes can evaporate over time, As they emit Hawking radiation, they slowly lose mass. For stellar mass black holes, this process would take an unimaginably long time, far longer than the current age of the universe. However, for tiny primordial black holes that might have formed in the early universe, this evaporation could be happening right now, providing a potential way to detect them. Hawking radiation and Cygnus X-1 are both connected to the fascinating realm of black holes, though in different ways. Hawking radiation, named after the renowned physicist Stephen Hawking, is a theoretical process by which black holes are thought to slowly emit particles and lose mass over time. This concept challenges the traditional view that nothing can escape a black hole's gravitational pull. Cygnus X-1, on the other hand, is a real-world example of a black hole that scientists can observe. It was one of the first strong candidates for a black hole ever discovered. Located in the constellation Cygnus, this cosmic object is part of a binary system where a massive blue supergiant star orbits around an invisible companion, the black hole. The connection between Hawking radiation and Cygnus X-1 lies in our understanding of black hole physics. While we cannot directly observe Hawking radiation from Cygnus X-1 due to its extremely faint nature, the study of this real black hole helps scientists refine their theories about black hole behavior, including the potential for Hawking radiation. Observations of Cygnus X-1 have provided valuable data about the properties of black holes, their interactions with surrounding matter, and the extreme physics at play in these environments. This information, in turn, helps physicists like Hawking develop and test theories about black hole behavior on quantum scales, where phenomena like Hawking radiation become relevant. Detecting Hawking radiation from Cygnus X-1 or any other black hole in our galaxy remains a significant challenge for modern astronomy. Cygnus X-1, a well-known binary system containing a stellar mass black hole, emits various forms of radiation that we can observe. However, Hawking radiation, the theoretical emission of particles from the event horizon of black holes, is incredibly faint and difficult to detect. The primary issue lies in the inverse relationship between a black hole's mass and the intensity of its Hawking radiation. Larger black holes, like the one in Cygnus X-1, which is estimated to be about 15 times the mass of our Sun, would emit Hawking radiation at an extremely low intensity. This makes it virtually impossible to distinguish from the background noise of space and other forms of radiation emitted by the black hole and its companion star. Furthermore, the radiation from the accretion disk surrounding Cygnus X-1, which is created by matter falling into the black hole, is much more intense and easily observable. This accretion disk radiation effectively drowns out any potential Hawking radiation, making detection even more challenging. While we cannot currently detect Hawking radiation from Cygnus X-1 or any other known black hole, the concept remains an important part of theoretical physics. Scientists continue to develop more sensitive detection methods and explore alternative ways to potentially observe this elusive phenomenon in the future. Hawking radiation fundamentally alters our perception of black holes as cosmic voids from which nothing can escape. This groundbreaking concept, proposed by physicist Stephen Hawking in the 1970s, suggests that black holes are not entirely black after all. Instead, they emit a faint glow of particles, slowly evaporating over time. This radiation arises from quantum effects near the event horizon, the boundary beyond which nothing can escape a black hole's gravitational pull. Quantum fluctuations create pairs of particles and antiparticles in this region. Occasionally, one particle falls into the black hole while the other escapes, appearing to an outside observer as radiation emitted by the black hole itself. The existence of Hawking radiation implies that black holes are not eternal. As they emit this radiation, they gradually lose mass and energy. Given enough time, even the most massive black holes will eventually evaporate completely. This concept challenges our classical understanding of black holes as cosmic sinkholes that only grow larger over time. Moreover, Hawking radiation raises intriguing questions about the nature of information in the universe. The apparent loss of information as matter falls into a black hole, combined with the eventual evaporation of the black hole itself, creates a paradox that continues to puzzle physicists and cosmologists to this day. Cygnus X-1, a stellar mass black hole in our Milky Way galaxy, faces a fascinating fate if Hawking radiation proves to be real. This process, theorized by the renowned physicist Stephen Hawking, suggests that black holes slowly emit particles over time, gradually losing mass and energy. For a black hole as massive as Cygnus X-1, which is about 15 times the mass of our Sun, the effects of Hawking radiation would be extremely slow. The larger a black hole, the cooler its temperature, and the slower it radiates. At its current size, Cygnus X-1 would take an unimaginably long time to evaporate, far longer than the current age of the universe. However, if we fast forward to the incredibly distant future, Hawking radiation would eventually cause Cygnus X-1 to shrink. As it loses mass, the rate of evaporation would accelerate. In the final moments of its existence, it would release an enormous amount of energy in a burst of radiation, effectively exploding and disappearing from the universe. This process highlights the dynamic nature of black holes and challenges our understanding of these cosmic enigmas. If Hawking radiation is indeed real, it suggests that even the most massive objects in our universe are not eternal, but subject to the fundamental laws of quantum mechanics and thermodynamics. Hawking radiation serves as a fascinating bridge between the realms of quantum mechanics and general relativity, two fundamental pillars of modern physics that have long resisted unification. This phenomenon, proposed by the renowned physicist Stephen Hawking, occurs at the event horizon of black holes, where the extreme gravitational effects described by general relativity meet the quantum fluctuations of empty space. At the quantum level, pairs of virtual particles constantly pop in and out of existence. Near a black hole's event horizon, one particle of the pair may fall into the black hole while the other escapes. The escaping particle becomes real, taking energy from the black hole in the process. This energy loss manifests as a faint emission of radiation from the black hole, now known as Hawking radiation. The existence of Hawking radiation challenges our classical understanding of black holes as objects from which nothing can escape. It suggests that black holes are not entirely black, but have a temperature and slowly evaporate over time. This process brings together quantum mechanics, which governs the behavior of particles at the smallest scales, and general relativity, which describes the curvature of spacetime by massive objects like black holes. Hawking radiation represents a crucial step towards a theory of quantum gravity, as it demonstrates how quantum effects can influence the behavior of gravitational giants like black holes. It highlights the need for a unified theory that can fully explain the interplay between quantum mechanics and gravity at all scales. The companion star to the black hole in Cygnus X-1 is a blue supergiant. This massive star, known as HDE 226868, is one of the brightest and most luminous stars in our galaxy. Blue supergiants are rare and short-lived, representing a brief phase in the life cycle of very massive stars. This particular blue supergiant is estimated to be about 40 times the mass of our Sun and has a surface temperature of around 30,000 Kelvin. Its immense size and high temperature cause it to emit a powerful stellar wind, which is partly captured by the nearby black hole. The interaction between this blue supergiant and its black hole companion creates a fascinating cosmic dance. As the supergiant loses mass to the black hole, it forms an accretion disk of superheated material swirling around the black hole. This process generates intense X-ray emissions, which is how Cygnus X-1 was first detected and identified as a potential black hole candidate. The study of this binary system has provided astronomers with valuable insights into the nature of black holes, stellar evolution, and the extreme physics of accretion processes. The blue supergiant companion plays a crucial role in making Cygnus X-1 one of the brightest X-ray sources in our sky, allowing scientists to study this remarkable system in great detail. The companion star plays a crucial role in shaping the behavior of a black hole in a binary system. As the two celestial bodies orbit each other, the immense gravitational pull of the black hole begins to strip away the outer layers of the companion star. This process, known as accretion, creates a swirling disk of gas and dust around the black hole. The material in this accretion disk doesn't immediately fall into the black hole. Instead, it spirals inward, heating up to extreme temperatures due to friction and compression. This superheated material emits intense radiation across the electromagnetic spectrum, making the binary system highly luminous and detectable from Earth. The rate at which the companion star loses mass to the black hole can vary, leading to fluctuations in the system's brightness and energy output. In some cases, the interaction between the black hole and its companion can trigger powerful outbursts or jets of material that are ejected at nearly the speed of light. The mass, size, and composition of the companion star also influence the overall behavior of the binary system. A larger, more massive star will provide more material for the black hole to consume, potentially leading to more dramatic and energetic events. This interplay between the black hole and its stellar companion creates a dynamic and ever-changing cosmic dance that astronomers continue to study and unravel. The companion star in a binary system faces a complex and often dramatic fate. As its partner evolves and expands, the companion star can be significantly affected. In many cases, the expanding star begins to transfer matter to its companion, altering the composition and structure of both stars. This process can lead to various outcomes depending on the initial masses and separation of the stars. One possible fate is that the companion star accretes so much matter that it becomes more massive than its original partner. This role reversal can dramatically change the evolution of both stars. In extreme cases, the companion might accumulate enough mass to explode as a supernova, leaving behind a neutron star or black hole. Alternatively, if the stars are close enough, they might eventually merge into a single larger star. This merger can trigger intense stellar events, potentially resulting in a luminous red nova or even a more powerful explosion. In some instances, the companion star might be completely engulfed by its expanding partner, leading to a common envelope phase that can eject large amounts of stellar material into space. For some companion stars, particularly those in wider orbits, the fate might be less dramatic. They might continue their stellar evolution relatively undisturbed, only to be left orbiting the remnant of their former partner, such as a white dwarf, neutron star, or black hole. The ultimate fate of the companion star thus depends on a delicate interplay of stellar physics, making binary star systems a fascinating subject of study in astrophysics. The companion star plays a crucial role in our study of black holes, acting as a cosmic detective that reveals hidden secrets. As the star orbits the black hole, its motion and behavior provide valuable clues about the nature of its invisible partner. Astronomers observe the companion star's orbit, which allows them to calculate the mass of the black hole with remarkable precision. The gravitational pull of the black hole affects the companion star in measurable ways. This interaction causes the star to move in a distinct pattern, which we can detect through spectroscopic observations. By analyzing the star's spectral lines, scientists can determine its velocity and how it changes over time, revealing the presence and properties of the unseen black hole. Furthermore, as the black hole pulls material from its companion star, this matter forms an accretion disk around the black hole. The intense heat generated by this process causes the disk to emit X-rays, which we can observe with space-based telescopes. These X-ray emissions provide additional data about the black hole's size, spin, and feeding habits. The companion star also helps us study how black holes affect their immediate surroundings. By observing changes in the star's appearance and behavior over time, scientists gain insights into the long-term effects of living in close proximity to these cosmic giants. This knowledge enhances our understanding of stellar evolution and the complex relationships between stars and black holes in binary systems. The companion star in this binary system exhibits several fascinating properties that set it apart from its more familiar counterpart. This celestial body is classified as a white dwarf, the dense remnant core of a star that has exhausted its nuclear fuel. Despite its small size, roughly comparable to Earth, it packs an enormous amount of mass into this compact volume, resulting in an object of extreme density. One of the most striking features of this white dwarf is its intense gravitational field. The force of gravity at its surface is about 200,000 times stronger than what we experience on Earth. This immense gravitational pull causes the companion star to warp the fabric of space-time around it, creating a cosmic arena for remarkable physical phenomena. The white dwarf also boasts an incredibly hot surface temperature, reaching upwards of 20,000 degrees Celsius. This scorching heat causes the star to emit a brilliant blue-white glow, a stark contrast to the reddish hue of its larger companion. Despite its high temperature, the white dwarf is gradually cooling over billions of years, a process that will eventually lead to its transformation into a cold, dark remnant known as a black dwarf. Another intriguing aspect of this companion star is its rapid rotation. Many white dwarfs spin at dizzying speeds, some completing a full rotation in mere minutes. This rapid spinning is a result of the conservation of angular momentum, as the star collapsed from a much larger size to its current compact form. These unique characteristics make the companion star a captivating subject for astronomical study, offering insights into the life cycles of stars and the extreme physics at play in the cosmos. The proximity of a companion star to a black hole dramatically alters its evolutionary path, creating a cosmic dance with profound consequences. As the companion orbits the black hole, intense gravitational forces begin to strip away its outer layers. This process, known as stellar stripping, causes the star to lose mass at an accelerated rate, significantly shortening its lifespan. The black hole's immense gravity also distorts the shape of the companion star, stretching it into an elongated form. This tidal distortion can lead to increased nuclear fusion rates within the star, causing it to burn through its fuel more rapidly than it would in isolation. The result is a star that ages prematurely, potentially evolving into a stellar remnant far sooner than its counterparts in less extreme environments. Furthermore, the material stripped from the companion star does not simply disappear. It forms an accretion disk around the black hole, a swirling maelstrom of superheated gas and dust. As this material falls towards the black hole, it releases enormous amounts of energy in the form of X-rays and other high-energy radiation. This radiation, in turn, can further influence the evolution of the companion star, potentially stripping away even more of its outer layers or triggering unusual chemical processes within its atmosphere. The interplay between the black hole and its stellar companion can also lead to periodic outbursts of energy and matter. These cosmic eruptions, often observed as X-ray novae or microquasars, represent yet another way in which the black hole shapes the life cycle of its neighboring star, creating a unique and dynamic stellar evolution scenario unlike anything seen in solitary star systems. Cygnus X-1 formed from the dramatic end of a massive star's life. This celestial object began as a colossal star, many times more massive than our Sun, born in a region of intense star formation. As the star aged, it rapidly consumed its nuclear fuel, leading to a series of transformations in its core. When the star exhausted its fuel, it could no longer support itself against the crushing force of gravity. In a matter of seconds, the star's core collapsed, triggering a supernova explosion. However, this particular star was so massive that even the force of the supernova could not overcome gravity's pull. The result was the formation of a black hole, with the remaining stellar material falling inward and becoming incredibly compressed. This newborn black hole, Cygnus X-1, continued to grow by consuming nearby gas and dust, as well as material from its binary companion star. Today, Cygnus X-1 exists as part of a binary system, constantly drawing material from its companion star. This process of material accretion generates intense X-ray emissions, making Cygnus X-1 one of the brightest X-ray sources in our galaxy and a fascinating subject for astronomers studying the extreme physics of black holes. The progenitor star that gave rise to Cygnus X-1 was a truly remarkable celestial object. This massive star, which existed millions of years ago, was likely more than 40 times the mass of our Sun. It would have been an extremely hot, bright, and powerful star, classified as an O-type blue supergiant. During its relatively short lifespan, this colossal star burned through its nuclear fuel at an incredible rate, shining with the brilliance of hundreds of thousands of suns. Its intense radiation and powerful stellar winds would have profoundly influenced its surrounding environment, shaping the interstellar medium and potentially triggering the formation of new stars. As this behemoth neared the end of its life, it underwent a series of dramatic changes. Its core, having exhausted its fuel, began to collapse under its own immense gravity. This collapse triggered a supernova explosion, blasting away the outer layers of the star. However, the core was so massive that not even the force of the supernova could overcome its gravity, leading to the formation of the black hole we now know as Cygnus X-1. The transformation of this once brilliant star into a black hole serves as a cosmic reminder of the intense forces at play in our universe, showcasing the extreme end states of stellar evolution and the birth of some of the most enigmatic objects in the cosmos. The Cygnus X-1 system is a fascinating cosmic duo that has captivated astronomers for decades. This remarkable binary system is estimated to be approximately 6 million years old. This age might seem ancient by human standards, but in cosmic terms, Cygnus X-1 is relatively young. Cygnus X-1 consists of a massive blue supergiant star orbiting a black hole. The black hole, one of the first ever discovered, formed from the collapse of an even more massive star. The age of the system has been determined through careful analysis of the properties of the visible star and the orbital characteristics of the pair. Interestingly, the age of Cygnus X-1 provides valuable insights into the evolution of massive stars and the formation of stellar mass black holes. It suggests that some stars can collapse directly into black holes without first exploding as supernovae, a process that astronomers are still working to fully understand. The youth of Cygnus X-1 also means that astronomers can observe it in a relatively early stage of its evolution, offering a unique opportunity to study the dynamics of binary systems containing black holes. This makes Cygnus X-1 an invaluable cosmic laboratory for testing theories of stellar evolution and general relativity. Cygnus X-1 offers valuable insights into the formation and behavior of black holes throughout the universe. As one of the closest known black holes to Earth, it serves as an excellent laboratory for studying these enigmatic cosmic objects. The study of Cygnus X-1 has revealed crucial information about the life cycles of massive stars and their eventual collapse into black holes. This system consists of a black hole orbiting a blue supergiant star, allowing scientists to observe the complex interactions between these two celestial bodies. By analyzing the radiation emitted from the accretion disk surrounding the black hole, researchers have gained a better understanding of how matter behaves in extreme gravitational environments. Observations of Cygnus X-1 have also provided evidence for the existence of event horizons, the boundary beyond which nothing can escape a black hole's gravitational pull. This finding supports the theoretical predictions of general relativity and helps confirm our understanding of black hole physics. Furthermore, the mass measurements of Cygnus X-1 have implications for black hole formation theories. Its substantial mass suggests that some black holes may form directly from the collapse of massive stars without first becoming neutron stars. This information helps refine our models of stellar evolution and the various pathways that can lead to the creation of black holes throughout the cosmos. Cygnus X-1 stands as a remarkable example of stellar evolution, showcasing the dramatic end stages of massive stars. This binary system consists of a blue supergiant star orbiting an incredibly dense object, which scientists have identified as a stellar mass black hole. The formation of Cygnus X-1 aligns with our current models of how the most massive stars in the universe evolve and die. The story of Cygnus X-1 begins with two enormous stars, each many times more massive than our Sun. These stars burned through their nuclear fuel at an accelerated rate due to their immense size. The more massive of the pair evolved faster, expanding into a red supergiant before ultimately exploding as a supernova. This cataclysmic event left behind a black hole with a mass approximately 15 times that of our Sun. The remaining companion star, now observed as the blue supergiant, continues to evolve. It loses mass to the black hole through stellar winds and occasional episodes of more intense mass transfer. This process not only feeds the black hole, but also generates the powerful X-ray emissions that led to the initial discovery of Cygnus X-1. Cygnus X-1 provides astronomers with a valuable opportunity to study black hole physics and the later stages of stellar evolution in real time. Its existence confirms theoretical predictions about the fate of very massive stars and helps refine our understanding of the processes that shape the most extreme objects in our universe. Cygnus X-1 has long been considered a prime example of a stellar mass black hole, but scientists have proposed several alternative theories to explain its nature. One intriguing hypothesis suggests that instead of a black hole, Cygnus X-1 could be an extremely dense neutron star. This theory posits that the object's immense gravitational pull and high energy emissions could be explained by a rapidly rotating neutron star with an incredibly strong magnetic field, known as a magnetar. Another alternative theory proposes that Cygnus X-1 might be a quark star, an even more exotic and hypothetical type of ultra-dense star. Quark stars are thought to form when the neutrons in a neutron star break down into their constituent quarks under extreme pressure. This would create an object with properties that could potentially mimic those of a black hole. Some researchers have also suggested that Cygnus X-1 could be a boson star, a theoretical object composed of bosons rather than fermions. Boson stars are predicted to have properties similar to black holes, but without an event horizon or singularity. This theory, while highly speculative, attempts to reconcile the observed characteristics of Cygnus X-1 with alternative models of compact objects. Despite these alternative theories, the majority of astronomical evidence still strongly supports the idea that Cygnus X-1 is indeed a black hole. Ongoing research and future observations with more advanced instruments may provide further insights into the true nature of this fascinating cosmic object. Gravitational waves are ripples in the fabric of spacetime that travel across the universe at the speed of light. These waves are produced when massive objects accelerate, such as when two black holes orbit each other and eventually merge. Albert Einstein first predicted the existence of gravitational waves in his theory of general relativity, but it took scientists nearly a century to directly detect them. These cosmic ripples carry information about the events that created them, allowing us to observe phenomena that are otherwise invisible to traditional telescopes. When gravitational waves pass through Earth, they cause minute changes in the distances between objects, stretching and squeezing space itself by incredibly small amounts. The first direct detection of gravitational waves occurred in September 2015, marking a groundbreaking moment in astronomy. This detection, made by the Laser Interferometer Gravitational Wave Observatory, or LIGO, opened up an entirely new way of observing the universe. Gravitational wave astronomy has since flourished, enabling scientists to study cosmic events like the mergers of black holes and neutron stars. This field continues to provide new insights into the nature of gravity, the properties of matter under extreme conditions, and the history of our universe. Cygnus X-1, a well-known black hole in our galaxy, is a prime candidate for producing gravitational waves. This cosmic powerhouse consists of a supermassive black hole orbited by a blue supergiant star. As these two massive objects dance around each other, they create ripples in the fabric of spacetime known as gravitational waves. The primary mechanism for gravitational wave production in Cygnus X-1 is the orbital motion of the black hole and its companion star. As they orbit, their immense gravitational fields interact and distort spacetime, sending out waves that travel at the speed of light across the universe. These waves carry energy and information about the system that produced them. Another potential source of gravitational waves in Cygnus X-1 is the accretion disk surrounding the black hole. As matter from the companion star falls towards the black hole, it forms a swirling disk of superheated gas. Irregularities or instabilities in this disk could produce additional gravitational waves, albeit likely weaker than those generated by the orbital motion. Detecting gravitational waves from Cygnus X-1 would provide valuable insights into the nature of black holes, the behavior of matter in extreme gravitational fields, and the fundamental properties of spacetime itself. While current detectors are not yet sensitive enough to pick up these signals, future upgrades and new observatories may soon bring us closer to unraveling the gravitational secrets of this cosmic giant. Gravitational waves from Cygnus X-1, a well-known black hole in our galaxy, are indeed theoretically detectable. However, current technology faces significant challenges in measuring these waves directly. Cygnus X-1 is a binary system consisting of a black hole and a blue supergiant star orbiting each other. As they orbit, they should produce gravitational waves, ripples in the fabric of spacetime. The frequency of these waves is too low for our current ground-based detectors like LIGO and Virgo to pick up. These detectors are optimized for higher frequency events like merging black holes or neutron stars. To detect the continuous, low-frequency waves from Cygnus X-1, we would need space-based detectors like the proposed LISA mission. LISA, or the Laser Interferometer Space Antenna, is designed to detect low-frequency gravitational waves. It consists of 3 spacecraft forming a triangle in space, using laser beams to measure minute changes in the distance between them caused by passing gravitational waves. Once operational, LISA could potentially detect the subtle waves from systems like Cygnus X-1. Detecting these waves would provide valuable information about the black hole's mass, spin, and orbit, offering a new way to study these enigmatic objects. It would also serve as an important test of general relativity in the strong gravity regime near black holes. Detecting gravitational waves from Cygnus X-1 would mark a significant milestone in our exploration of black holes and the fundamental laws of physics. Cygnus X-1 is a well-known binary system consisting of a black hole and a blue supergiant star. By capturing gravitational waves from this system, scientists could gain unprecedented insights into the behavior of matter and spacetime in extreme gravitational environments. These observations would allow us to test general relativity in ways never before possible. We could examine how gravity behaves near the event horizon of a black hole, potentially uncovering new physics or confirming existing theories. The data could also provide valuable information about the mass, spin, and other properties of the black hole in Cygnus X-1 with extraordinary precision. Furthermore, studying the gravitational waves from this system could shed light on the complex interactions between the black hole and its companion star. We might learn more about how black holes accrete matter and how this process affects the surrounding spacetime. This knowledge could have far-reaching implications for our understanding of astrophysical processes and the evolution of binary star systems. Ultimately, detecting gravitational waves from Cygnus X-1 would open up a new window for observing the universe, complementing traditional electromagnetic observations and potentially revealing hidden aspects of cosmic phenomena. It would represent a powerful tool for probing the nature of gravity and the structure of spacetime, pushing the boundaries of our knowledge in fundamental physics and cosmology. The search for gravitational waves from systems like Cygnus X-1 primarily relies on large-scale interferometers. These sophisticated instruments are designed to detect the incredibly subtle ripples in spacetime caused by massive cosmic events. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, is at the forefront of this search. LIGO consists of 2 detectors located in the United States, one in Hanford, Washington, and the other in Livingston, Louisiana. Each LIGO detector uses laser beams traveling along perpendicular arms, each about 4 kilometers long. These lasers are precisely monitored for any changes in their interference patterns, which could indicate the passage of a gravitational wave. The detectors are so sensitive they can measure changes smaller than the width of a proton. Working in tandem with LIGO is the Virgo detector, located near Pisa, Italy. Virgo operates on the same principles as LIGO, but with slightly shorter arms at 3 kilometers. The collaboration between these detectors allows scientists to triangulate the source of gravitational waves more accurately. Another instrument in this cosmic search is KAGRA, the Kamioka Gravitational Wave Detector, located underground in Japan. KAGRA is unique because it operates at cryogenic temperatures to reduce thermal noise, potentially allowing it to detect even fainter signals. These advanced instruments work together in a global network, constantly listening for the faint whispers of gravitational waves from distant cosmic events, including those from systems like Cygnus X-1. Cygnus X-1, a binary star system containing a black hole, has played a crucial role in advancing our understanding of gravitational waves. This system, located about 6,000 light-years from Earth, consists of a blue supergiant star orbiting a black hole roughly 15 times the mass of our Sun. The study of Cygnus X-1 has provided valuable insights into the behavior of binary systems containing black holes, which are prime sources of gravitational waves. By observing the interactions between the black hole and its companion star, scientists have refined their models of how these systems evolve and eventually merge, producing powerful gravitational wave signals. Furthermore, Cygnus X-1 has served as a testbed for theories of general relativity and gravity in strong field regimes. The extreme gravitational environment near the black hole allows researchers to probe the limits of our understanding of gravity, helping to validate or refine theoretical predictions about gravitational wave generation and propagation. The detailed observations of Cygnus X-1 have also improved our ability to estimate the population and characteristics of binary black hole systems in the universe. This knowledge is crucial for gravitational wave astronomy, as it helps scientists predict the frequency and types of gravitational wave events we can expect to detect with current and future observatories. The Cygnus X-1 system, a famous binary star system, holds a fascinating future. This celestial pair consists of a blue supergiant star and a black hole locked in a cosmic dance. As time progresses, the supergiant will continue to lose mass to its hungry black hole companion through a process called accretion. Eventually, in approximately 1 to 2 million years, the blue supergiant will exhaust its nuclear fuel. When this happens, the star will undergo a spectacular supernova explosion, briefly outshining its entire home galaxy. The fate of this explosion is intriguing. It may result in the formation of a second black hole, or it could produce a neutron star. If a second black hole forms, Cygnus X-1 will become an even rarer cosmic object, a binary black hole system. These systems are of great interest to scientists studying gravitational waves. On the other hand, if a neutron star emerges, it will create a black hole neutron star binary, another exotic and scientifically valuable cosmic pairing. Regardless of the outcome, the Cygnus X-1 system will continue to be a source of fascination for astronomers. Its future evolution will provide valuable insights into the life cycles of massive stars, the formation of compact objects, and the dynamics of binary systems in the universe. The black hole in Cygnus X-1 will undergo a fascinating evolution over cosmic timescales. As it continues to feed on its companion star, the black hole will gradually increase in mass. This process of accretion will cause the event horizon, the boundary beyond which nothing can escape, to expand slowly outward. Over millions of years, the black hole's intense gravitational pull will continue to strip material from its stellar partner. This ongoing feast will not only fuel the growth of the black hole, but also lead to changes in the binary system's dynamics. The orbit of the companion star will likely decay, bringing it closer to the black hole and potentially accelerating the rate of mass transfer. As the companion star eventually exhausts its fuel, it too may collapse, potentially forming a second black hole. This could result in a binary black hole system, a rare and intriguing cosmic phenomenon. Alternatively, if the companion star is not massive enough to form a black hole, it might become a neutron star or white dwarf, orbiting the much larger black hole. In the incredibly distant future, spanning billions of years, the black hole in Cygnus X-1 might merge with other black holes, or grow to become a supermassive black hole at the heart of a galaxy. However, Such long-term predictions are highly speculative and depend on numerous factors in the cosmic environment. As the companion star depletes its fuel, a dramatic series of events unfolds that will reshape the binary system. The star will begin to expand, becoming a red giant, as it burns through its remaining hydrogen. This swelling process will cause the star to lose mass, some of which may be captured by its neutron star partner. The neutron star, with its immense gravitational pull, will start to draw more material from the expanding companion. This process, known as accretion, will cause the neutron star to spin faster and potentially emit more intense radiation. The influx of matter onto the neutron star could lead to powerful X-ray emissions and even occasional bursts of energy. Eventually, the companion star will shed its outer layers, leaving behind a white dwarf or, if it was massive enough, undergo a supernova explosion. In the case of a supernova, the system could be disrupted entirely, potentially freeing the neutron star to travel through space alone. If a white dwarf remains, the two stellar remnants might continue orbiting each other, their dance slowed but not ended. This transformation of the binary system showcases the dynamic nature of stellar evolution and the complex interactions between stars in close proximity. The fate of the companion star and its neutron star partner illustrates the ongoing cycle of stellar life and death in our universe. Cygnus X-1, a well-known black hole located approximately 6,000 light-years from Earth, poses no immediate or foreseeable danger to our planet. This cosmic behemoth, with a mass estimated at about 15 times that of our Sun, is simply too far away to have any direct impact on Earth or our solar system. The primary reason for this lack of threat lies in the vast distances involved in space. Even though black holes exert tremendous gravitational forces, these forces diminish rapidly with distance, following the inverse square law. At 6,000 light-years away, the gravitational influence of Cygnus X-1 on Earth is negligible. Moreover, black holes do not actively hunt or suck in matter from great distances. They only capture objects or material that comes very close to their event horizon. Our solar system, including Earth, is in a stable orbit around the center of the Milky Way galaxy, far from the reach of Cygnus X-1. While Cygnus X-1 continues to fascinate scientists as an excellent subject for studying black hole physics, it remains a distant observer in the cosmic theater, posing no threat to our blue planet. The real danger it presents is purely academic, challenging our understanding of extreme gravitational environments and the nature of spacetime itself. Cygnus X-1 will remain a crucial object of study for astronomers and astrophysicists for many decades to come. This remarkable cosmic entity, a binary system consisting of a blue supergiant star and a black hole, continues to provide invaluable insights into the nature of extreme gravitational environments and the behavior of matter under intense conditions. As our observational technologies advance, we can expect to gather even more detailed data about Cygnus X-1. Future space telescopes and improved ground-based instruments will allow scientists to probe deeper into the system's dynamics, potentially revealing new aspects of black hole physics and the processes of stellar evolution. The longevity of Cygnus X-1 as a research target is also tied to its role in testing and refining our theories of general relativity. As one of the closest known black holes to Earth, it serves as an ideal cosmic laboratory for studying gravitational effects in the strong field regime. This makes it an essential tool for verifying predictions of general relativity and exploring potential deviations that might point to new physics. Moreover, Cygnus X-1 will continue to be important in our quest to understand the formation and evolution of binary systems containing black holes. By studying its properties over extended periods, scientists can gain insights into the long-term behavior of such systems, which in turn informs our understanding of galactic evolution and the life cycles of massive stars. As we continue to study Cygnus X-1, one of the most famous black holes in our galaxy, astronomers anticipate several exciting discoveries in the coming decades. Advanced telescopes and improved detection methods could reveal new details about the black hole's event horizon, the point of no return from which nothing can escape. Scientists hope to capture more precise images of the matter swirling around Cygnus X-1, potentially unveiling the intricate structures of its accretion disk. Researchers also expect to gain a deeper understanding of how Cygnus X-1 interacts with its companion star. By observing the system over extended periods, we might uncover patterns in how the black hole pulls matter from its stellar partner, shedding light on the complex dance between these two cosmic objects. This could provide valuable insights into the life cycles of massive stars and the formation of black holes. Furthermore, advancements in gravitational wave detection might allow us to pick up signals from Cygnus X-1. If successful, this could offer a new way to study the black hole's properties, including its spin and mass, with unprecedented accuracy. Such measurements would not only enhance our knowledge of Cygnus X-1, but also contribute to our broader understanding of black hole physics. Lastly, long-term observations might reveal unexpected phenomena, such as changes in the black hole's behavior or its effects on the surrounding space. These discoveries could challenge our current theories and open up new avenues of research in astrophysics, potentially revolutionizing our understanding of these enigmatic cosmic objects. Cygnus X-1 has been a subject of intense study for astronomers since its discovery in 1964. Multiple telescopes and observatories, both on Earth and in space, have been employed to unravel its mysteries. Radio telescopes play a crucial role in observing Cygnus X-1. The Very Large Array in New Mexico has been instrumental in mapping the radio emissions from this cosmic powerhouse. The European Very Long Baseline Interferometry Network, which combines data from multiple radio telescopes across the globe, has provided high-resolution images of the system. In the realm of space-based observatories, NASA's Chandra X-ray Observatory has been pivotal in studying the high-energy emissions from Cygnus X-1. The Hubble Space Telescope has also contributed by observing the visible light from the companion star in the system. More recently, NASA's NewStar mission has focused on the hard X-ray emissions, providing new insights into the black hole's behavior. Ground-based optical telescopes like the Gemini Observatory and the Very Large Telescope in Chile have also played their part, studying the visible light from the system and its surroundings. These diverse observational tools, working in concert, have allowed scientists to build a comprehensive understanding of Cygnus X-1, from its accretion disk to its powerful jets. Space-based observatories have revolutionized our understanding of Cygnus X-1, providing crucial insights into this fascinating cosmic object. These advanced telescopes, operating above Earth's atmosphere, can detect a wide range of electromagnetic radiation that would otherwise be blocked or distorted by our planet's protective layers. Cygnus X-1, a binary system consisting of a blue supergiant star and a black hole, emits powerful X-rays and gamma rays. Space observatories like the Chandra X-ray Observatory and the Fermi Gamma Ray Space Telescope have captured these high-energy emissions with unprecedented clarity. This has allowed scientists to study the intense gravitational forces and extreme physics at play around the black hole. These observations have revealed the complex interactions between the black hole and its companion star. Space-based instruments have detected the hot, swirling disk of material being pulled from the star towards the black hole, as well as powerful jets of particles ejected from the system. By analyzing the energy and patterns of these emissions, researchers have gained new insights into how matter behaves in the presence of incredibly strong gravitational fields. Furthermore, space observatories have enabled more precise measurements of Cygnus X-1's mass and spin. This data has helped refine our models of black hole formation and evolution, contributing to our broader understanding of these enigmatic cosmic objects and their role in shaping the universe. Astronomers studying Cygnus X-1 encounter several significant challenges due to the nature of this remarkable cosmic object. As a binary system containing a black hole, Cygnus X-1 emits powerful X-rays and other high-energy radiation that cannot penetrate Earth's atmosphere. This means ground-based telescopes are unable to directly observe much of the radiation coming from the system. To overcome this obstacle, astronomers must rely on space-based observatories equipped with specialized X-ray detectors. However, these orbital telescopes have their own limitations, including smaller sizes compared to Earth-bound instruments and the need for periodic maintenance or replacement. Another challenge lies in the extreme brightness of Cygnus X-1. The intense radiation can overwhelm sensitive detectors, making it difficult to study finer details of the system's structure and behavior. Astronomers must carefully calibrate their instruments and often use clever observational techniques to gather meaningful data without saturating their equipment. The dynamic nature of Cygnus X-1 also poses challenges. The system's brightness can vary dramatically over short timescales, requiring coordinated observations from multiple telescopes to capture its full range of behaviors. This complexity makes it challenging but rewarding for astronomers seeking to unravel the mysteries of black holes and their effects on surrounding matter. Our ability to observe Cygnus X-1 has dramatically improved since its discovery in 1964. Initially detected as a powerful source of X-rays during a rocket flight, this celestial object puzzled astronomers for years. Early observations were limited to basic X-ray and radio wave detections, providing only rudimentary information about its nature and behavior. As technology advanced, so did our understanding of Cygnus X-1. The launch of more sophisticated X-ray telescopes in the 1970s and 80s allowed scientists to study its emissions in greater detail. These observations revealed the object's intense variability and helped confirm its identity as a black hole in a binary system with a blue supergiant star. The advent of space-based observatories in the late 20th and early 21st centuries marked a significant leap forward. Instruments like the Chandra X-ray Observatory and the XMM Newton telescope provided unprecedented views of Cygnus X-1, capturing high-resolution images and spectra. These advanced tools enabled scientists to study the accretion disk surrounding the black hole and the powerful jets of material it ejects. Most recently, the development of gravitational wave detectors has opened up an entirely new way of observing Cygnus X-1. While we have not yet detected gravitational waves from this specific system, the technology now exists to potentially do so in the future, which could provide invaluable insights into the physics of black holes and the nature of gravity itself. Future technologies promise to revolutionize our observations of Cygnus X-1, the famous black hole system in the constellation Cygnus. Advanced space-based telescopes with improved X-ray and gamma-ray detectors will allow us to peer deeper into the extreme environment around this cosmic giant. These instruments will capture higher resolution images and more precise spectral data, revealing intricate details of the accretion disk and the powerful jets emanating from the black hole. Gravitational wave detectors, both on Earth and in space, will offer a new window into the dynamics of Cygnus X-1. By measuring tiny ripples in spacetime, these detectors could potentially observe oscillations in the black hole's event horizon or capture signals from any smaller objects orbiting nearby. This would provide unprecedented insights into the black hole's properties and the nature of spacetime itself. Quantum sensors and next-generation adaptive optics systems will enhance our ability to study Cygnus X-1 across multiple wavelengths. These technologies will help us filter out atmospheric distortions and cosmic noise, resulting in clearer, more detailed observations of the black hole and its companion star. Advanced data processing techniques, powered by machine learning algorithms, will allow scientists to extract even more information from these improved observations. Interferometry networks, combining data from multiple telescopes across the globe and in space, will create virtual telescopes with extraordinary resolving power. This could potentially allow us to directly image the immediate vicinity of Cygnus X-1's event horizon, much like the first image of a black hole captured by the Event Horizon Telescope. Such observations would provide crucial tests of general relativity and our understanding of black hole physics in extreme gravitational environments. Multi-wavelength observations of Cygnus X-1 have revolutionized our understanding of this famous black hole system. By studying Cygnus X-1 across different parts of the electromagnetic spectrum, astronomers have pieced together a comprehensive picture of its structure and behavior. In visible light, we see the massive blue supergiant star that orbits the black hole. Ultraviolet observations reveal the hot gas being stripped from this companion star. Moving into X-rays, we detect the innermost regions of the accretion disk, where material spirals towards the black hole at incredible speeds, heating up to millions of degrees. Radio observations show us powerful jets of material being ejected from the system, stretching out for light years into space. These jets are formed by complex interactions between the black hole, the accretion disk, and magnetic fields. By combining data from all these wavelengths, scientists can model how matter and energy flow through the Cygnus X-1 system. This multi-wavelength approach has allowed astronomers to measure the black hole's mass and spin with unprecedented accuracy. It has also revealed how the black hole's powerful gravity and intense radiation affect its surroundings, providing a natural laboratory for testing theories of extreme physics. Near Cygnus X-1, we encounter some of the most extreme conditions in the known universe. This celestial object is a binary system consisting of a blue supergiant star and a black hole locked in a cosmic dance. The black hole, with a mass about 15 times that of our Sun, creates an environment of unimaginable intensity. The gravitational pull of the black hole is so strong that it strips away the outer layers of its companion star. This material forms a swirling disk of superheated gas around the black hole, reaching temperatures of millions of degrees. As this gas spirals inward, it accelerates to nearly the speed of light, releasing enormous amounts of energy in the form of X-rays. The boundary of the black hole, known as the event horizon, marks a point of no return. Beyond this threshold, the gravitational force is so intense that not even light can escape. The fabric of spacetime itself becomes severely warped, and our conventional understanding of physics breaks down. Cygnus X-1 also produces powerful jets of particles that shoot out from its poles at nearly the speed of light. These jets extend for thousands of light years, interacting with the surrounding interstellar medium and creating shock waves that can be detected from Earth. The extreme conditions near Cygnus X-1 provide scientists with a unique laboratory for studying the behavior of matter and energy under the most intense gravitational fields in the universe. Cygnus X-1 serves as a cosmic laboratory for studying matter under extreme conditions. This binary system consists of a blue supergiant star orbiting a black hole, providing scientists with a unique opportunity to observe the behavior of matter in intense gravitational fields. As material from the companion star falls toward the black hole, it forms an accretion disk. This disk becomes superheated due to friction and intense gravitational forces, reaching temperatures of millions of degrees. The extreme heat causes the disk to emit powerful X-rays, which we can detect and analyze from Earth. These X-ray emissions allow scientists to study the properties of matter as it approaches the event horizon of the black hole. The strong gravitational field near Cygnus X-1 also enables researchers to test predictions of general relativity. By observing how light and matter behave in this extreme environment, scientists can verify or challenge our understanding of fundamental physics. Additionally, the system provides insights into the formation and evolution of black holes and their effects on surrounding space. Cygnus X-1 thus offers a window into conditions that cannot be replicated in Earth-based laboratories, making it an invaluable resource for advancing our knowledge of astrophysics and the nature of the universe under the most extreme circumstances. Cygnus X-1 offers a unique laboratory for studying the extreme physics of black holes and their effects on space and time. As one of the closest known black holes to Earth, it provides astronomers with an exceptional opportunity to observe and analyze these cosmic phenomena. The intense gravitational pull of Cygnus X-1 warps the fabric of spacetime around it, creating a region where our conventional understanding of physics breaks down. By studying the behavior of matter and energy near this black hole, scientists can test and refine theories about gravity, relativity, and quantum mechanics. Observations of Cygnus X-1 have revealed intriguing effects predicted by Einstein's theory of general relativity. The black hole's immense gravity causes time dilation, where time passes more slowly near the black hole than it does for distant observers. This effect becomes more pronounced closer to the event horizon, the point of no return beyond which nothing can escape the black hole's pull. Furthermore, Cygnus X-1 helps scientists explore the concept of frame dragging, where a rotating black hole drags the very fabric of spacetime around with it. This phenomenon affects the motion of nearby objects and the behavior of light, providing valuable insights into the nature of space, time, and gravity in the most extreme environments in the universe. Cygnus X-1 stands as a cosmic enigma that challenges our understanding of physics at its most extreme. This powerful X-ray source, located roughly 6,000 light-years from Earth, is believed to be a black hole of stellar mass. Its very existence pushes our theories to their limits, forcing scientists to grapple with the nature of space, time, and matter in ways previously unimagined. The immense gravitational pull of Cygnus X-1 creates an environment where the laws of physics as we know them begin to break down. Here, the fabric of spacetime is stretched and warped to such an extent that our conventional understanding of reality is called into question. The black hole's event horizon, the point of no return beyond which nothing can escape its grasp, represents a boundary not just in space, but in our scientific knowledge. Observations of Cygnus X-1 have revealed phenomena that strain our current models of black hole behavior. The system's powerful jets, which shoot out particles at nearly the speed of light, challenge our understanding of how matter and energy interact in such extreme conditions. These jets, along with the intense X-ray emissions from the accretion disk surrounding the black hole, provide a unique laboratory for testing theories of general relativity and quantum mechanics. Furthermore, Cygnus X-1 offers insights into the life cycles of massive stars and the formation of black holes. By studying this system, astronomers hope to unravel the mysteries of stellar evolution and the fundamental forces that shape our universe. As we continue to observe and analyze Cygnus X-1, it remains a crucible for refining our physical theories, pushing us ever closer to a more complete understanding of the cosmos. Cygnus X-1, the first black hole ever discovered, continues to challenge our understanding of physics. To fully explain this enigmatic object, scientists may need to develop new theories that bridge the gap between general relativity and quantum mechanics. One area of exploration involves the behavior of matter in extreme gravitational fields. Current models struggle to accurately describe how gas and plasma behave as they spiral into the black hole's event horizon. New physics might be required to explain the complex interactions between the intense gravity, magnetic fields, and high-energy particles in this environment. Another frontier is the nature of the event horizon itself. Some theories suggest that quantum effects could create a firewall of energy at the boundary, challenging our classical understanding of black holes. Developing a complete theory of quantum gravity could provide insights into these phenomena and help explain the observed properties of Cygnus X-1. Lastly, the jets of material ejected from the black hole's poles present another mystery. While we have some understanding of how these jets form, the mechanisms behind their incredible speeds and energy remain unclear. New physics might be needed to fully explain how black holes like Cygnus X-1 accelerate particles to near light speed and maintain these powerful outflows over vast distances. Cygnus X-1, a binary star system containing a black hole, serves as a cosmic laboratory that enhances our understanding of the early universe in several ways. This system, located roughly 6,000 light-years from Earth, provides crucial insights into the formation and behavior of black holes, which were abundant in the universe's infancy. By observing Cygnus X-1, scientists can study how matter behaves under extreme gravitational conditions. This knowledge helps us model the environment around supermassive black holes that existed in the early universe, influencing the formation and evolution of galaxies. The intense X-ray emissions from Cygnus X-1 also offer clues about the high-energy processes that were common in the young cosmos. Furthermore, the study of Cygnus X-1 aids in refining our understanding of stellar evolution. The black hole in this system formed from a massive star, similar to those that populated the early universe. By analyzing its properties, scientists can better estimate the masses and types of stars that existed in the cosmic dawn, as well as how they might have influenced their surroundings. Cygnus X-1 also serves as a testbed for theories of general relativity in strong gravitational fields. These tests help validate our models of how gravity behaved in the dense environment of the early universe, contributing to a more complete picture of cosmic history from its earliest moments to the present day. The discovery of Cygnus X-1 in 1964 marked a turning point in our understanding of black holes and stellar evolution. This powerful X-ray source, located in the constellation Cygnus, provided the first compelling evidence for the existence of black holes, which were previously considered purely theoretical objects. Cygnus X-1 consists of a binary star system where a blue supergiant orbits an invisible companion. Through careful observations and calculations, scientists determined that this unseen object was too massive to be a neutron star, leaving a black hole as the only plausible explanation. This realization opened up new avenues of research in astrophysics, prompting scientists to search for and study other potential black hole candidates. The study of Cygnus X-1 has also advanced our knowledge of accretion processes, where matter from the companion star falls into the black hole, creating a swirling disk of superheated material. This accretion disk emits intense X-rays, which we can detect and analyze from Earth. By studying these emissions, scientists have gained insights into the behavior of matter under extreme gravitational conditions. Furthermore, Cygnus X-1 has served as a crucial testbed for general relativity, allowing researchers to verify Einstein's predictions about the behavior of space and time near extremely massive objects. The ongoing study of this system continues to push the boundaries of our understanding of the universe, inspiring new theories and observations in the field of astrophysics. The study of Cygnus X-1 has been a catalyst for numerous advancements in astrophysics and our understanding of black holes. This binary star system, consisting of a blue supergiant star and a black hole, has opened up exciting new avenues of research in several key areas. One significant area of study is the behavior of matter in extreme gravitational fields. Cygnus X-1 provides a unique laboratory for observing how gas from the companion star behaves as it falls into the black hole. This has led to improved models of accretion disks and the complex processes that occur near the event horizon of a black hole. The system has also spurred research into the formation and evolution of binary star systems containing black holes. Scientists are now investigating how such systems come to exist and how they change over time. This research has implications for our understanding of stellar evolution and the life cycles of massive stars. Furthermore, Cygnus X-1 has been instrumental in advancing our knowledge of relativistic jets. These powerful outflows of matter and energy from the vicinity of the black hole have become a subject of intense study, leading to new insights into the mechanisms behind these phenomena and their impact on the surrounding space. Cygnus X-1 has revolutionized our understanding of stellar evolution and the exotic objects that can result from it. This powerful X-ray source, first discovered in 1964, initially puzzled astronomers with its intense emissions and rapid variability. As observations improved, scientists realized they were witnessing something extraordinary. The first strong candidate for a black hole in our galaxy. The story of Cygnus X-1 begins with a massive star, over 40 times the mass of our Sun, that exhausted its nuclear fuel and collapsed. Instead of exploding as a supernova, this stellar giant left behind a black hole, an object so dense that not even light can escape its gravitational pull. This black hole, with a mass of about 15 times that of our Sun, is locked in a cosmic dance with a blue supergiant star, forming a binary system. This discovery challenged previous notions about the end stages of stellar evolution. It provided compelling evidence that some massive stars could indeed collapse directly into black holes without a supernova explosion, a process theorized but never before observed. Cygnus X-1 also helped confirm the existence of stellar mass black holes, bridging the gap between theory and observation in astrophysics. Furthermore, Cygnus X-1 has served as a cosmic laboratory for studying extreme physics. The interaction between the black hole and its companion star creates an accretion disk of superheated gas, allowing scientists to study matter under extreme conditions of temperature, density, and gravity. These observations have provided invaluable insights into the behavior of matter near black holes and the mechanisms behind the powerful jets of energy often associated with these enigmatic objects. Cygnus X-1, a binary star system containing a black hole, has significantly influenced our understanding of galaxy formation and evolution. This cosmic powerhouse has provided crucial insights into the role of supermassive black holes in shaping galaxies. The study of Cygnus X-1 has revealed that black holes can grow by accreting matter from their surroundings, a process that releases enormous amounts of energy. This energy output can profoundly affect the surrounding gas and dust, either triggering or suppressing star formation in galaxies. By observing Cygnus X-1, scientists have gained a better grasp of how these processes might scale up to the supermassive black holes at the centers of galaxies. Furthermore, Cygnus X-1 has helped astronomers refine their models of how matter behaves in extreme gravitational environments. These models have been applied to understand the dynamics of galactic cores where supermassive black holes reside. The interactions between these central black holes and the surrounding galactic material play a crucial role in determining the overall structure and evolution of galaxies. The existence of Cygnus X-1 also supports the idea that stellar mass black holes, formed from the collapse of massive stars, are common throughout galaxies. This prevalence suggests that black holes of various sizes have been influencing galactic evolution throughout cosmic history, contributing to the diverse range of galaxy types we observe today. Cygnus X-1, the first strong black hole candidate ever discovered, has had a profound impact on multiple scientific disciplines. Its study has not only revolutionized our understanding of astrophysics, but has also influenced fields far beyond the realm of space science. In the domain of physics, Cygnus X-1 has provided a natural laboratory for testing theories of gravity. The extreme gravitational environment near the black hole has allowed scientists to probe the limits of general relativity, Einstein's groundbreaking theory. This has led to advancements in our understanding of spacetime and the behavior of matter under intense gravitational forces. The technology developed to study Cygnus X-1 has found applications in medical imaging. The high-energy X-ray detection methods used to observe the black hole have been adapted for use in computed tomography scans, improving diagnostic capabilities in healthcare. Additionally, the data processing techniques developed to analyze the complex signals from Cygnus X-1 have been applied to fields such as telecommunications and signal processing. In the field of materials science, the study of accretion disks around Cygnus X-1 has inspired research into new states of matter. The extreme temperatures and pressures in these disks have led scientists to investigate how materials behave under similar conditions on Earth, potentially leading to the development of new materials with unique properties. Cygnus X-1 has been a crucial laboratory for understanding black holes and their behavior. This stellar mass black hole, locked in a binary dance with a blue supergiant star, has taught us valuable lessons that we can apply to other extreme objects throughout the cosmos. One key insight from Cygnus X-1 is the process of accretion, where matter from the companion star falls towards the black hole, forming a swirling disk of superheated material. This phenomenon is not unique to Cygnus X-1, but occurs in various systems, from quasars powered by supermassive black holes to neutron stars in binary systems. The study of accretion in Cygnus X-1 has helped astronomers better understand how matter behaves in extreme gravitational environments across the universe. Cygnus X-1 has also shed light on the production of powerful jets of particles and energy that shoot out from the poles of some black holes. These relativistic jets, observed in Cygnus X-1, are also seen in other systems like active galactic nuclei and gamma-ray bursts. The mechanisms behind jet formation and propagation studied in Cygnus X-1 can be applied to understand similar processes in more distant and powerful cosmic objects. Furthermore, the detailed observations of Cygnus X-1 have allowed scientists to test and refine theories of general relativity in strong gravitational fields. These lessons are invaluable when studying other extreme objects, such as neutron stars, magnetars, and even larger black holes, where the fabric of spacetime is severely warped. The knowledge gained from Cygnus X-1 continues to inform our understanding of gravity and matter in the most extreme conditions the universe has to offer. Cygnus X-1, the first black hole candidate ever discovered, has captured the imagination of science fiction writers and creators for decades. This cosmic powerhouse has been featured in various forms of media, often serving as a backdrop for thrilling space adventures or as a central element in mind-bending plots. In literature, Cygnus X-1 has been portrayed as a gateway to other dimensions or distant parts of the universe. Some stories depict brave explorers venturing near its event horizon, experiencing time dilation and other relativistic effects. Other tales imagine advanced civilizations harnessing the immense energy of the black hole for interstellar travel or as a power source for megastructures. Television and film have also embraced Cygnus X-1 as a setting for space opera narratives. It has been depicted as a dangerous navigational hazard for starships, a hiding place for space pirates, or a location for secret research facilities studying exotic physics. Some productions have even imagined the black hole as a sentient entity capable of communication or manipulation of its surroundings. Music has not been left out of the Cygnus X-1 fascination. The progressive rock band Rush famously created a two-part epic inspired by the black hole, weaving together themes of science, mythology, and human exploration. This musical interpretation has further cemented Cygnus X-1's place in popular culture, bridging the gap between scientific discovery and artistic expression. Cygnus X-1 has played a pivotal role in shaping our understanding of black holes and bringing these enigmatic cosmic objects into the public consciousness. As the first strong candidate for a black hole ever discovered, Cygnus X-1 captured the imagination of scientists and the general public alike when it was identified in 1971. This celestial system, located roughly 6,000 light-years from Earth, consists of a massive blue supergiant star orbiting an invisible companion. The intense gravitational pull and X-ray emissions from this unseen object provided compelling evidence for the existence of stellar mass black holes, which had previously been purely theoretical constructs. The discovery of Cygnus X-1 sparked intense scientific debate and public interest, leading to increased funding and research into black holes and related phenomena. It served as a crucial observational anchor for theoretical work on general relativity and the behavior of matter in extreme gravitational fields. This, in turn, has greatly advanced our understanding of the life cycles of massive stars and the formation of black holes. Beyond the scientific community, Cygnus X-1 has become a cultural touchstone, appearing in science fiction literature, music, and popular media. Its study has helped bridge the gap between abstract theoretical physics and observable astronomical phenomena, making the concept of black holes more tangible and accessible to the public. This increased awareness has fueled curiosity about the universe and inspired a new generation of scientists to explore the mysteries of the cosmos. Cygnus X-1 has indeed captured the imagination of artists and creators, finding its way into popular culture. One of the most famous musical tributes to this cosmic object comes from the Canadian rock band Rush. They dedicated an epic two-part song to Cygnus X-1, released on their 1977 album, A Farewell to Kings. The song, titled Cygnus X-1, explores themes of black holes and space travel, blending scientific concepts with poetic lyrics. In literature, Cygnus X-1 has been mentioned in various science fiction novels and short stories. While not always the central focus, it often serves as a backdrop or reference point for stories involving black holes or extreme cosmic phenomena. Its mysterious nature and powerful gravitational pull make it an ideal subject for writers exploring the wonders and dangers of space. The world of cinema has also taken notice of Cygnus X-1. Although not frequently featured as a main plot element, it has been referenced in several science fiction films and documentaries about space. Its appearance in these works often serves to illustrate the concept of black holes or to provide a sense of scale and wonder about the universe. Cygnus X-1's presence in these various forms of media highlights its significance in both scientific and popular understanding of black holes. Its role in art and entertainment has helped bring complex astronomical concepts to a wider audience, sparking curiosity and wonder about the mysteries of our universe. Cygnus X-1 has captivated artists and writers since its discovery, serving as a wellspring of creative inspiration. This celestial object, a binary system consisting of a blue supergiant star orbiting a black hole, has become a symbol of the mysterious and awe-inspiring nature of our universe. Many science fiction authors have incorporated Cygnus X-1 into their narratives, using it as a backdrop for tales of interstellar travel and exploration. The intense gravitational pull of the black hole often serves as a plot device, creating tension and danger for characters venturing too close to its event horizon. Some writers speculate about the possibility of using the black hole's immense energy as a power source for advanced civilizations or as a gateway to other dimensions. Visual artists have also been drawn to Cygnus X-1, attempting to capture its essence in various mediums. Paintings and digital artworks often depict the black hole as a swirling vortex of darkness, surrounded by the vibrant blue light of its companion star. These visual interpretations help bring the concept of a black hole to life for audiences who may struggle to grasp such an abstract astronomical phenomenon. Musicians, too, have found inspiration in Cygnus X-1. Perhaps most famously, the progressive rock band Rush created a two-part epic song cycle based on the black hole, blending scientific concepts with mythological themes. This fusion of science and art demonstrates how Cygnus X-1 has transcended its status as a mere astronomical object to become a cultural touchstone, bridging the gap between scientific understanding and artistic expression. Cygnus X-1 has been a beacon of inspiration for astronomers and physicists since its discovery in 1964. As the first strong candidate for a black hole, it sparked intense scientific debate and drove researchers to push the boundaries of our understanding of the universe. This cosmic object challenged existing theories and forced scientists to confront the reality of extreme gravitational phenomena. The study of Cygnus X-1 led to significant advancements in our knowledge of stellar evolution, accretion processes, and the behavior of matter in intense gravitational fields. These discoveries have inspired countless young minds to pursue careers in astrophysics and related fields. The ongoing research into Cygnus X-1 continues to yield new insights, demonstrating the importance of long-term observational studies. Its role in confirming the existence of black holes has been crucial in shaping our modern view of the cosmos, influencing everything from theoretical physics to popular culture. For many aspiring scientists, Cygnus X-1 represents the exciting frontier of space exploration and the potential for groundbreaking discoveries. It serves as a reminder that the universe still holds many mysteries waiting to be unraveled, motivating future generations to continue pushing the boundaries of human knowledge. Cygnus X-1 has captured the public imagination since its discovery in 1964. Initially, this powerful X-ray source was a mysterious entity, sparking speculation about its true nature. As our understanding of black holes grew, Cygnus X-1 became increasingly associated with these enigmatic cosmic objects. In the 1970s, Cygnus X-1 gained fame beyond scientific circles when it was immortalized in song. The rock band Rush released a two-part epic titled Cygnus X-1 on their album A Farewell to Kings, weaving a science fiction narrative around the black hole. This marked a significant moment in popular culture, bringing astrophysical concepts to a wider audience through music. As technology advanced, visual representations of Cygnus X-1 evolved dramatically. Early depictions were often artistic interpretations, showing a dark void surrounded by swirling matter. With the advent of sophisticated computer simulations, these images became more scientifically accurate, revealing the complex interactions between the black hole and its companion star. Recent years have seen a surge in public interest in black holes, partly due to groundbreaking scientific achievements like the first direct image of a black hole. While that image was not of Cygnus X-1, it reignited fascination with these cosmic phenomena, including our galactic neighbor. Today, Cygnus X-1 continues to feature in documentaries, science fiction, and educational materials, serving as a tangible example of the extraordinary objects that populate our universe.